All right, let's go ahead and get started. If there's still troubleshooting, then I'm going to step out in the hallway and we can take care of that and figure it out on the side. Professor Andrew Ferguson is Assistant Professor of Material Science and Engineering here at UIUC, and he's an affiliated Assistant Professor of Chemical and Biomolecular Engineering, as well as Computational Science and Engineering. He received his PhD in Chemical and Biological Engineering from Princeton University in 2010 and commenced his appointment at UIUC in August 2012. His research interests lie at the intersection of material science, molecular simulation, and machine learning, with principal foci on machine learning-enabled understanding and design of self-assembling biomaterials and bioinformatics inference of statistical mechanical models of viral fitness. Other areas of interest include global graph matching, accelerated sampling, and nonlinear inference of protein folding landscapes. And then last semester is when you taught the 498.
That's right.
Okay. So he taught a 498 course introducing tools of computational material science, which ran over LAMMPS and GROMACS and
Quantum espresso,
and a lot of the sorts of tools that are involved here. So watch for that if his 498 comes up in the future and you're interested in learning more about those tools as well. So I'll turn it over to you.
All right, thank you, Neil. So yeah, thank you very much for inviting me. It's a great pleasure to be here. And so today it's sort of a dual session. So the first half, maybe sort of 40, 45 minutes, I thought I'd just give a general introduction to molecular dynamics, you know, what the algorithm is, what the fundamental theory is. And then the second portion will be sort of a hands-on portion where we're going to do some calculations on aluminum to compute cohesive energies, Young moduli, things like that. So using the LAMMPS package that Neil has made available for download. And so I thought I'd just keep this very informal, and so if there's any questions as we go along, please do raise your hand. I think we should have plenty of time. And you know, if you feel like there's something I haven't covered in enough detail, please just do stick your hand up. Okay, so let's get started. So just to sort of orient ourselves, molecular dynamics are sort of the time and land scales accessible are sort of in the nano range, so nanometers and nanoseconds. If you want to do things that are much bigger or much smaller, you need to use a completely different algorithm. And so this is sort of the place where we're at. I think tomorrow Lucas Wagner and Elif Ertica and David Sepperly are going to talk about things down in this land scale. So we're a little bit bigger than that. And so what's the best way to think about molecular dynamics? And so I think there are at least three ways I find useful to think about it. Maybe the most useful one, the most sort of intuitive one, is a computational microscope. And so it's like we're looking at atoms and molecules, but instead of using microscopy, we're using computational methods. And so we're building the laws of physics into our computer, watching things evolve, and we're sort of watching atoms move in silico, if you like. You might also like to think of it as an experiment on a computer. We build all the laws of physics, we design our system, and then we let it run and see what happens. And so in that sense, it's an in silico experiment. And basically what we're doing, it's sort of one of the dumbest algorithms around, is that we're integrating Newton's equations of motion on the microscale. And so basically F equals ma is everything. Of course, there's lots of bells and whistles beyond that as to, you know, how you actually make the simulation efficient and run properly. But that's the fundamental idea. And so why is it useful? Well, basically we can gain atomistic insight into sort of structure and kinetics. And so there are super advanced experimental techniques that allow you to do an excellent job of visualizing sort of individual atoms, but typically techniques even at the cutting edge are sort of static in the sense that you can't watch the dynamics of atoms very well. So that's one benefit of molecular simulation, is you can really get the dynamics. You can also predict and understand, and so you can work in tandem with experiment. You can make testable predictions, or you can help rationalize experimental observations. And one of the nice features of molecular simulations, you have total control of all of the molecular features. So if you want to ask such absurd questions in an experimental lab as what would happen if I turned off electrostatics, that's something that's basically impossible to do, but in computer simulations, of course, you have control over that, and you can test ideas such as that. And so subject to available force fields and computational power, basically we can get all classical thermodynamics about any molecular system. And so obviously that's an oversell. We're limited in the times and land scales that we can simulate, but computers are getting faster and faster, and so the systems we can tackle are getting bigger and bigger. So what sorts of things might we investigate using molecular dynamics? So materials property prediction, which is probably the most interesting focus for the folks in this room. So you can compute things from basically first principles, at least at the classical level. Bulk moduli, surface tensions, thermal conductivities. If you're interested in biomaterials or biomolecular simulations, you can fold proteins, look at ion transport. If you're looking at drug design, and this is one of the most sort of commercialized uses of molecular dynamics, is looking for ligand docking or high throughput screening of drug candidates. That's something that's very well established now. And so if you go to the Northeast Corridor in New Jersey, Merck, all those folks, they have R&D labs they have people running molecular dynamics simulations to try and isolate drug candidates. And so computer power just continues to follow Moore's law. Whether that's going to hold in the near future or not is a matter of contention. But it's certainly true that computation is getting cheaper and cheaper every year. And molecular simulations are becoming more reliable and more validated. And so that's to say that if you can do some, certainly not all, but some of your testing in silico, you can massively reduce the costs of research and development. So Ford Motor Company recently had a nice test case study when they were designing a new component for one of their new cars, and they tried to do sort of 50% of the design in silico, and it turned out they sort of compressed the time scale to development by about 50%, and it was also about 50% cheaper. And so incorporating these sort of molecular simulation methods into industrial things is really becoming very popular. And so on the academic side, I'm just sort of trying to illustrate that it's also used in academia if that's your interest. That as a function of year, the number of papers citing molecular dynamics, so not a perfect metric, but we're sort of seeing exponential growth. And I don't know what happened here. This was perhaps the oversell and then the bump, but certainly this is rising. It's becoming a commercial tool and an academic tool to do research and industrial design. Okay, so I thought I'd just give you a couple slides on the history. So when was it born? So it was born in the late 50s. Bernie Alder and Dwight, I think, Wainwright invented molecular dynamics and performed the first simulation of a hard sphere fluid. And so basically programmed a computer, which was a painful process in those days, to simulate the hard sphere dynamics. And so going from the solid to the liquid vapor. And so Bernie Alder is currently emeritus at UC Davis, and he received the National Medal of Science and the Boltzmann Medal for this work. And so he really gave birth to this entire field. And just some milestones to see where we are. And so this is back at its birth, and so 1957. A few years later, we simulated radiation damage to copper. So that's something that we do nowadays, actually. There are folks in the material science department here, Pascal Ballon, Bob Averbeck, who are simulating radiation damage to materials today using much more advanced methods, of course, but the principle is the same. And then moving forward, we started simulating more realistic things, liquid argon, liquid water. And then a lot of the sort of firepower and the money in molecular simulation nowadays is on sort of the biomolecular side rather than the materials side, for whatever reason. And so David Shaw, you may know his investment firm, D.E. Shaw. He's an adjunct professor at Columbia, and he has this giant building in Manhattan. And the bottom half of the building is sort of financial instruments, and the top half are a bunch of folks running molecular dynamics on proteins, and he spends all his money, it's sort of his hobby, to do molecular dynamics. And so he currently holds the record. He's done a millisecond simulation of this BPTI protein in water. So it's sort of a heroic thing. He has this beautiful machine called Desmond and this custom code and everything. It's really quite remarkable. Okay, and so with that, let's start talking about the basic principles that we're going to use today in the hands-on session. And so, like I said, MD is really sort of a super simple algorithm. We're just simulating atomic motions using classical mechanics. And so I like to think of running a simulation like cooking. And so this was inspired by something Alexei Aksimentiev, who's in the physics department here, said during one of his talks. That just think about following the recipe. So basically, there are three ingredients. And so the first thing you need is an initial system configuration. So if you're simulating a solid metal or an alloy, you need the positions of all the atoms, the initial velocities of all the atoms, and that's your initial conditions. You then need an interaction potential. So how do the atoms talk to one another? So what are the ways the atoms interact? Is it Lennard-Jones? Is it Coulombic? Are there bonded interactions? And so we'll talk a little bit about that. And then basically it just reduces to a way to numerically integrate force equals mass times acceleration. And you need to be careful about the way you do that, but basically it's just a numerical integration that we're all familiar with. And so before we move on, I like to sort of draw this analogy with back in the 1700s or early 1800s with Pierre-Simon de Laplace, who sort of thought about molecular dynamics before computers were even invented. And he said, you may be familiar with Laplace's demon, that if you had a vast intelligence who could comprehend all the forces by which nature is animated, so that's the force field, the V in the previous slide, and if you could figure out the respective positions of all the particles in the universe, and then analyze this data, you would be able to know the entire future and past of the universe. And so of course quantum mechanics tells you that that's not quite true, but it's close to being true, and that's basically molecular dynamics. And so this was preempted by Laplace. Okay, and so everything I'm going to, sorry, this laser pen is not working very well. Everything I'm going to talk about today is classical. And so we're going to hear tomorrow about some quantum mechanics. And so what is it that allows us to treat things classically? Why do we think that we don't need to worry about electronic effects? And so it turns out it is a valid description of the dynamics for at least two reasons. And so number one, the Born-Oppenheimer approximation allows us to treat electrons implicitly. And so you can think about the classical potential that we use to model the nuclear interactions as sort of having the electronic effects baked into it. And so frequently the way you develop a classical potential is to run quantum mechanical simulations and then extract some sort of a classical parameterization from your quantum mechanical results. And so in that sense, the electronic effects are within that. So you can also think about it as a separation of time scales, so the classic Born-Oppenheimer approximation. We're not going to worry about 10 to the minus 18 seconds, we're going to worry about 10 to the minus 15 seconds. The electrons are equilibrated to the nuclear positions. Perhaps the other way to think about it is using the de Broglie wavelength. And so the Schrodinger equation is basically how things really evolve. We're replacing that with Newton's equation, force equals mass times acceleration. And it turns out the de Broglie wavelength for all atoms except the very lightest ones is much, much smaller than the characteristic atomic separation of about an angstrom. And so for all but sort of hydrogen, we can really treat particles as point particles and not worry about the electronic effects. And the way one typically treats hydrogen in molecular dynamics simulations using classical potentials is to fix the bond length using a restraint, or actually just sort of lump the hydrogen atoms together with the heavier atom that they're bonded to. So frequently you'll see this so-called united atom description. So in alkanes, instead of having a carbon with a bunch of hydrogens hanging off it, you'll just have this lumped entity called a united atom that has the carbon and the hydrogens condensed together. So we don't really worry about the hydrogen effects. So of course, if you think those things are important, molecular dynamics is not the tool for you. You're going to need to use something like an electronic structure calculation. But if you're worried about longer time and length scales, then you can't get to that using electronic methods, so molecular dynamics is a useful tool. Okay, so let's just run through the three ingredients. So the first one I said was going to be the initial configuration. So we need to specify the initial atomic coordinates and velocities. And so classical mechanics, as we all know, is deterministic. And so the initial state and the interaction potential specifies the entire future and the entire past. So of course, we're integrating things numerically. There's going to be accumulation of errors. But in principle, we have a deterministic algorithm. So that's important for at least a couple of reasons. Number one, we believe that the simulations should be reproducible. So if you give your initial coordinates to somebody and your interaction potential, they should be able to reproduce your results. But the other part of that, sort of the flip side of the coin, is in order to perhaps get meaningful results, you might need to run a bunch of different simulations from different initial conditions to get something that's statistically meaningful, rather than just one single long trajectory starting from a single initial state. Okay, and so Laplace said if we have a vast intelligence and you told them all the parameters of the universe and the force field, they could figure out the entire future and the past. We don't have such a vast intelligence, or at least I don't, and so I have to use a computer to do it. So we're going to resort to numerical simulation. So how do you initialize your coordinates? So if you have a relatively simple thing, like maybe a perfect crystal, you can just go into MATLAB or even Excel and just build your coordinates and initialize your velocities. And so relatively simple. So things like liquid argon and bulk aluminum, you can just generate that sort of by hand if you like. For more complicated things, maybe proteins or crystals, metals, alloys with structural defects, you might need to use some tool to sort of help you generate that. And so there are a bunch of tools here for helping you generate the structures. And if you're a biomolecular, a biomaterials person, you can actually download from the protein database coordinates for the protein that you might be interested in. And so they're online and available. And so Neil, are we going to post these slides, or can we post these slides?
I'm happy to post
Okay, so we can post these things if you guys are interested in grabbing the links instead of having to write that down. Okay, so that's the coordinates. How do you set the velocities? And so you might think the simplest thing to do is just initialize everybody with a zero velocity. And so that's okay. It turns out it's not a great thing to do, because as soon as you start your molecular simulation, you typically attach a thermostat to it, and so there's going to be a large thermal shock to your system. And so typically what one wants to do is randomly draw velocities from the Maxwell-Boltzmann distribution, so the equilibrium distribution you would expect at the temperature of interest. And so that's a very simple way of just assigning initial velocities to your system and making your initial part of your simulation more stable. Okay, so that's part one, pretty simple, positions and velocities. Part two, now we need to ask how the atoms and the molecules talk to one another. And so the net force acting on each atom is a result of its interactions with everybody else in the system. So formally, this is an n squared problem, and so it's sort of expensive to compute. There are a number of tricks that we use, using cutoffs, etc. We believe that in a condensed phase, you're going to have some sort of cutoff radius beyond which you have a screening effect. You don't really have to worry about atoms that are really far away. So in that sense, we have a benefit over the astrophysics folks who don't have sort of the screening length. And so that's a benefit for us. And so the interaction potential is known as a force field or an interaction potential, so that goes by a couple of different names. And really this is one of the biggest sort of development areas, at least in academia, for molecular systems, is there are groups. So the one that springs to mind immediately is Ilja Siepman, who's up in Minnesota. There are a number of groups all over the world who just spend a lot of time and a lot of effort and a lot of sort of hard thinking about how to develop transferable and robust force fields. And so you'd like to know that the force field you download from the internet that's been parameterized at 298K in 1 atmosphere is perhaps useful at, say, 350K or 500K or 12 atmospheres. And so you'd like it to be transferable in that sense, so you can make predictions beyond where it was just parameterized. And so there are a number of folks all over the world, and so for metals, these are the ones we're going to be talking about today. The EAM and the MEAM potential are going to be the ones that we're most familiar with. For biomolecules, there's N different force fields, alkanes, water, and then sort of more generalized potentials. And so we're thankful to all these folks for developing them, and the parameters are all typically freely available for us to use. So you just pick the right one for the system you're interested in. And the great thing is about the modern molecular dynamics codes is these are already built into the code, so we don't have to worry about sort of parameterizing them by hand, which is a nice time-saving feature. Okay, so we have a potential function. So how do we actually use that to evolve the system in time? And so it's typically a very complicated function. And so, like we said, it's n squared, and it involves lots of different terms, sort of Coulombic, Leonard-Jones, etc., bonded terms. And so we have to sort of simulate numerically rather than analytically. And a question back there?
Yeah, I just was curious about whether you can treat this way these can be bonds that are directional, interactions that are more directional.
Absolutely. So we're going to come to that very shortly. But yeah, great point. And so, so in biomolecules, things are highly directional. So in proteins, and actually in crystals, you can sometimes have directional bonding as well. And so we'll definitely touch on that. Okay, so I give you V, or sort of, one of those groups on the previous slide gives you V. And so how do you then turn that into a force on an atom? Well, you just take the gradient. And so taking this del operator, the negative gradient of the potential is going to give you the force. Then this is sort of the heart of the algorithm. From the force, we can get accelerations, and we can evolve our system in time. And so we typically break the potential energy into a bunch of contributions. And so this is, of course, a gross approximation. Perhaps it's not perfectly broken down this way. It typically works pretty well. That we can treat things as bonded, and so, covalent or ionic bonds. Non-bonded, Leonard-Jones or Coulombic. Restraints, like I mentioned earlier, perhaps we want to pin hydrogen atoms because we don't want them oscillating like crazy. And field effects, so perhaps we have a solvent or a magnetic or an electric field that we want to worry about. And so let's just briefly look at each of those terms. And so this is touching on sort of directional things. And so maybe we have a bond, and so maybe we want things to remain a certain distance apart, and so we can build a potential that tells the system it has to do that. We can have a planar angle, we can have dihedral angles, and we can have improper dihedral angles, which is sort of out of plane bending. And so all of these things are very important for things like proteins and DNA if you're a biomaterials person. And they go by typically pretty simple forms. And so bonds are typically modeled as harmonic springs, as are planar angles. Product or a sum of cosines for the dihedral angles, and again a harmonic thing for the improper dihedrals. And so relatively simple things. So why are they simple? Well, because we're calling this force update every single step in our simulation. So we don't want to be looking up huge lookup tables or very complicated functions. And so typically folks try and use the simplest thing they can get away with. And these all work actually surprisingly well given their simplicity. So non-bonded, Van der Waals, so Leonard-Jones and Coulomb are the two big ones, and those are encoded into the force fields as non-bonded contributions. And one of the tricks that we use here is typically to decompose things as pairwise additive. And so that meaning that you just look at all your neighbors, compute your interaction with them, and add them all together. We don't typically want to worry about 3, 4, 5 body effects, again, because it makes the potential so much more complicated and so much more difficult to compute. So if you can get away with pairwise additive, then that's great. And as we'll see in some of these metal potentials, the EAM and the MEAM, we sort of break that a little bit, and they become a little bit more expensive to simulate because we have to worry about multi-body effects. And then fields. Okay, so there might be external potentials, electric, magnetic, or even a flow field we want to build in. Or there could be some sort of continuum effects. So if you want to do a continuum solvation, so say you're simulating a DNA molecule in water, formally you should put all the water molecules around it, but maybe that's going to be so expensive you can never simulate more than, say, a few femtoseconds. And so perhaps you want to say, well, okay, I'm willing to take a hit on accuracy, and I'm going to model the solvent just as a field. And so using something like the generalized Born approximation. And so you can build those into force fields. Okay, and so let's look at the force fields we're going to be using today. And so we're actually going to be using an EAM potential, which, as you may be familiar with if you do any of these things for a living, stands for the embedded atom model. And then there's the MEM potential, which is the modified embedded atom model. And so these were both developed by Mike Vasquez in the 80s and really ever since. And so the form of the EAM potential is, actually both of them, we'll talk about the differences in the next slide, looks like this. And so the total energy, this is the V function that we talked about earlier, it just goes by the name E for energy, is a sort of pairwise additive part here. And so you ask every atom in your crystal, what's your distance to every neighbor, and then you have some sort of potential that says, what effect do you feel from that neighbor? So typically that's something like a Leonard-Jones. And then you have this multibody part here, which is the so-called embedding function, which is a function of the local electronic density. And so if you're in a part of your crystal with lots of atoms around you, you have a high electronic density, and then this embedding potential tells you the multibody sort of impact of that. So that goes beyond pairwise things. It turns out pairwise is not good enough for most metals. And because of that, because of this term here, EAM is typically 2 times slower than Leonard-Jones, which is purely pairwise additive, and MEM, which I'll show you in the next slide, is about 3 to 5 times slower. And so we do take a performance hit because of this. But you really need to do this extra multi-body thing in order to get reasonable answers. Okay, so what's the difference between EAM and the modified EAM? And so the EAM potential, we don't have any directionality, so that goes back to the question here, that the embedding function is just a function of sort of the local density of electrons in your vicinity. In the MEM potential, we actually have some directionality. So it's not just the local density, we actually worry about sort of radial and angular contributions. And so the reason for this is it's very hard to simulate crystals with complex structures, so HCP, diamond, things like that, with just the EAM potential. We actually need to worry about the directionality of bonds in the crystal. And the MEM can give you that. And so you're going to need this for things like BCC, HCP, diamond. We're going to look at FCC aluminum today, in which case we can get away with an EAM. But you should be aware that for more complex architectures, you might need something like a MEM. Okay, so the good news is that these are all sort of consolidated in a repository online, hosted by NIST. And so we're actually going to go to this website later on today and download a potential. But basically, if you direct your browser to this link, you can scroll down, you see this big periodic table, and you just click on the atom that you're interested in, and you can see all the different EAM and MEM potentials that are available for that. If you scroll down a little further, you can see that there are a bunch of alloys, compounds, and mixtures. And so you can download EAM and MEM potentials that have sort of more than one component. And those files play well with a lot of molecular simulation engines. So LAMMPS can immediately recognize the format of those files, and you can just import it, and you're off to the races. Okay, so any questions about potential functions before we move on to the third ingredient? Okay, so integrators. So we have our initial positions and velocities. We believe we have a good approximation for how the atoms talk to one another. And so now we just need to compute the forces, get the accelerations, and then we can start time stepping using F equals ma. Okay, and so analytical solutions are unavailable for anything but sort of two-body things, and so this has been known since the time of Newton, Kepler, Galileo, all those guys, that you can only do an analytical solution for a two-body. So if you have a multi-body system, so more than 2 atoms, you need to resort to a numerical integration, and computers are perfectly suited to this sort of repetitive calculation. And so solving by hand would require thousands of years. In principle, it could be done, but we're going to appeal to the computer to speed things up for us. So many algorithms exist. So if you've done any sort of numerical integration, you know the simplest thing you can do is sort of an Euler integration, and we all know that that's sort of a bad thing to do in a lot of cases. So we use things like Runge-Kutta or Gear predictor corrector. So there's all these fancy integration algorithms one might want to use. And so it turns out that the one you should use, and almost, well, I think every actually molecular dynamics package does use, is a very simple one called the Verlet algorithm. And so it's one of the simplest integration algorithms. We don't use any of the more complex, fun things up here. It's It's super simple, it's very fast, it's very low memory, it's very stable, it's time reversible, and it's got this important feature known as being symplectic. And so what that means is it conserves volume and phase space. So it means that you're not sort of corrupting the volume that you explore as your simulation progresses. So it's sort of a technical issue, but the big deal about that is it means that it conserves energy really well. And so you have very poor accuracy for long time steps. So Runge-Kutta, Beeman, Newmark do great by allowing you to take a big time step. But over the long run, those complex algorithms actually add or remove energy from your system, which is a very bad thing. Whereas the Verlet algorithm does a really nice job of preserving your energy. And so it's much closer to what classical mechanics tells you should be doing. So again, this dates back, the first recorded use is by D'Alembert in 1791. It was repopularized in the 60s as molecular dynamics came to the fore. And it's super simple. And so you basically just take your Taylor series, you take a forward difference, you take a backward difference, and then you turn that into a central difference. And that's your Verlet algorithm. So what's great about that is it's super fast, it's super simple. So it means that applying it repetitively is very easy. And you get an order quartic error term in the positions and a squared error term in the velocities, which is good enough as long as your time step is small enough. So delta t is your time step there. So let's just compare its performance to some of these more complex algorithms. And so what I'm showing you in this plot here is the energy conservation, basically the error you make in the energy as a function of time. Leapfrog is just another name for Verlet, basically. And you see that it pins the energy very nicely. So of course it fluctuates on short time scales, but over the long run it's pinned very well. If you use a more complex algorithm, you get these drift terms. And so your system is sort of doing strange things that are not respecting the laws of classical mechanics. So use the Verlet algorithm. You have no choice, basically. You have to use the Verlet. Okay, so now we have the positions, velocities, we have the interaction potential, we know how we're going to integrate. So how do we run a simulation? And so this is how basically all simulations in the world run. Initialize positions and velocities. In your initial sort of configuration, you calculate all the forces using the potential. You do some fancy things on top of that we're going to talk about a little bit later. So maybe you don't just want to do F equals ma, but you actually want to add a thermostat or add a barostat so that you can simulate things in the canonical or sort of MPT ensembles where you have constant temperature or constant pressure. You then update all the positions and the velocities, and then you repeat. And so that's one time step, and then typically do millions and millions of time steps around this loop. And then we generate a trajectory, and so we see how the atoms evolve in time. And then the real sort of science comes in the analysis of that trajectory. So you set up your experiment in silico, you run it on the computer, and then you analyze your results. So it's very much like doing an experiment in the lab. So you need to be smart about the way you set up your system, and you need to be smart about the way you set up your data. Sort of the dullest part is actually just running this over and over again on your computer for as long as you can bear. Okay, so maybe to go in a little more detail, maybe not to hammer it to death, but you start with your initial situation, your initial configuration. Every atom has a position and a velocity. You look at atom 1, you ask how it's interacting with all other atoms in the system and compute the net force on that atom. You then turn that net force into an acceleration, and then you repeat that for every other atom in the system, so atom 2, 3, 4 through n. Once you have all the accelerations, you can update the positions and the velocities, and then you just repeat. And so the system is going to evolve in time in this discrete way. And we typically take time steps of around 1 to 2 femtoseconds. If you take any bigger than that, your system loses stability. If you take time steps any shorter than that, you're sort of just wasting compute cycles. It turns out that the sweet spot is around a femtosecond.
In molecular dynamics, atoms are typically represented.
So I thought I'd just show this quick movie. It's about a minute long, which just sort of recapitulates all the points here with some nice graphics. And so we have a little speaker here, so hopefully it's going to be loud enough.
In molecular dynamics, atoms are typically represented as single point masses inside van der Waals potentials. And what were the 612 potentials typically used to represent such things? This means that they come out mostly as hard spheres. Partial charges are then calculated via some form of quantum method to represent the distribution of electronic charge on those molecules. For a polar molecule like water, these partial charges can actually be quite large, with the best part of a full formal negative charge on the oxygen atom. In molecular dynamics, bonds are typically represented as simple harmonic oscillators, as are the angular constraints. To start the simulation, a range of velocities is chosen that matches the Boltzmann distribution for that temperature, and then those velocities are assigned randomly to each atom. Similar methods are then used to put energy into the bonds, angles, and dihedrals. The simulation is then run according to Newtonian physics, with the molecules transferring both energy and momentum to one another via electrostatics and van der Waals interactions. So in these simulations, water is essentially a hard sphere with 3-point charges in it. Surprisingly, such a simple method for modelling these systems gives surprisingly good results on numerous physical properties that can be calculated. Maybe the best of these is the structure. So if we plot the average probability of finding an oxygen in a unit volume with distance out from a specific water molecule, we get what we would call a radial distribution function. Now it turns out these structural functions can actually be measured directly via experimental methods such as neutron scattering. As you can see, these very simple methods do an okay job of modelling the structure of water. Now we can also...
So that was sort of focused on water, but the ideas are very similar for metals, which is what we're going to do with the hands-on stuff today. And so that was basically the simple introduction to molecular dynamics. We're going to touch on a few advanced things like thermostats, barostats, stuff like that. But basically that's the fundamentals of the algorithm. So are there any questions so far on anything that we've covered? Okay, then, sorry, question.
What is it about the distributions? If you took your atoms and you looked at a little bit your species and looked a little bit farther apart, so they had more potential energy, and you let it go, it's going to then be at a higher temperature than you think it was starting with conditions. So do you go back and check that then to make sure that the temperature is exactly what you had set it up to be?
Yes, that's a great point. And so if you do only what I've described so far, which is F equals MA, that's exactly what's going to happen. So formally you're going to be in sort of what's known as the NVE ensemble. And so if you start with a high potential energy and they prefer to be a little closer, the potential is going to get turned into kinetic and the system's going to heat up. The way you treat that is to couple the system to a thermostat. And so what you do is you integrate the equations of motion for the atoms and then you actually couple those equations to a hypothetical thermostat that sort of takes energy in or out of the system depending on its temperature.
Isn't it a thermal bath?
You can do it in multiple ways. One of the simplest ways is the thermal bath. Perhaps the simplest way is actually to rescale the velocities. And so if your velocities go out of a certain window, you can rescale them back in. There are more advanced ways of doing that. Actually, that's one of the things we're going to talk about right now.
How do you choose the temperature? The time step?
So the time step is sort of set by the scale of your system. And so we freeze out typically the fastest oscillations, which are sort of sub-femtosecond oscillations of very light atoms. And so by freezing them out, the shortest time scale typically are bending motions. And so the force field tells you what the harmonic potential is going to be for your bends, and you can compute a characteristic time step for that, and you need to be sort of 5 to 10 times shorter than that. If you take time steps longer than that, your system goes unstable. And so for almost every force field that I'm aware of, the right time step to take is 1 to 2 femtoseconds. If you're looking at coarse-grained potentials, so for example, if you want to do really long polymer chains, perhaps you don't want to simulate every single atom along the backbone, you could lump the atoms together. Those potentials are somewhat softer, and so that allows you to take a bigger time step. And so basically it's set by the force field, but a good rule of thumb is about a femtosecond. Okay, so let's just touch on some advanced topics, and we're going to be using some of these ideas today. And so the first one is if you just do F equals MA, if you've taken any sort of statistical thermodynamics or statistical mechanics, you'll be familiar with these horrible words. But we're in the NVE ensemble. So N meaning we have a fixed number of atoms, V meaning that we have a fixed volume, and E meaning we have a fixed energy. So that goes exactly back to this question. If you start your system in sort of a bad configuration with lots of potential energy, that's going to get turned into kinetic energy, and your system's going to heat up. And so what about if we want to do something closer perhaps to reality, to something we could measure in the laboratory, perhaps at constant temperature or constant pressure? So we need to operate in a different ensemble. So the canonical ensemble, NVT, so instead of fixed energy we have fixed temperature, NPT, instead of fixed volume we have fixed pressure, or MPH, which is sort of less common, which is isenthalpic. MD, essentially most most variants of MD are restricted to a fixed number of atoms, and so MD does not do very well when you have different numbers of atoms. So if you want to simulate something like adsorption onto a surface with a fixed chemical potential, you typically want to use something like Monte Carlo. Molecular dynamics is not great at that. So just a caveat. So how do we deal with a thermostat? Okay, and so we can compute the kinetic energy. We can just go into our simulation at every time step and ask each atom what its velocity is. We can then sum those and get the kinetic energy for the system, and then just use the equipartition theorem, because we're in classical mechanics, so these things typically hold pretty well, provided you're at equilibrium, to compute the temperature. You can then do a number of things. So the simplest thing you can do, as I sort of alluded to earlier, is just rescale all your velocities such that your temperature is what you want it to be. It turns out that doesn't sort of reproduce the fluctuations of your system very well, because you're sort of imposing this very hard constraint every time step. And so other things you can do is couple it to a bath. And so that's what the Berenzon and Anderson thermostats are doing. It's sort of coupling to a thermal bath. So if your atoms are too hot, they sort of give up energy to this fictitious thermal bath. If they're too cold, they take energy. And basically what that means is the velocities sort of go up and down. So you can think about coupling it almost through a harmonic spring to this thermal bath is the right way of thinking about it. It turns out the best way to do things is actually this so-called Nosey-Hoover thermostat. And so I don't want to get into the details of this. It's sort of very technical, but it's basically weak coupling to a bunch of fictitious oscillators. So outside your system, completely fictional, you have a bunch of oscillators at the correct temperature, and you couple them to the equations of motion for your atoms. And that actually reproduces two things, the temperature that you want, and actually it reproduces the fluctuations you would expect in reality as well. And so the variance of your temperature. And so the Nosey-Hoover is the right thing to use, and that's the one that we're going to use in the simulations we're going to do later on together. Barostats, very similar. So the expressions are a little more complicated, but it turns out the pressure comes from the so-called virial expression, which is this strange product between all the atom pairwise distances and forces. Don't worry about it, LAMMPS is going to calculate it for us. But basically we can do exactly the same trick. We can measure the pressure that actually exists in our system by doing this computation. Then we can see how good we are, and if we're off, we want to couple to sort of a pressure bath, if you like, so very similar. Or you can couple to this so-called Parnell-Raman barostat, which is sort of the analog of the Nosey-Hoover in the last slide, and that reproduces the fluctuations very well as well. And so again, fictitious oscillators that we're going to couple to the equations of motion. And so these are all built into all modern simulation codes, and so you just have to pick the right one. And so I guess the take home from here is that you can do thermostating and barostating, and typically you want to pick Nosey-Hoover and Parnell-Raman. Okay, so one of the other biggest issues is periodic boundary conditions. And so we can't simulate the entire universe. There are too many atoms. We have to simulate a little patch of space, which is typically nanometers across. And so if we want to simulate something that's in the bulk, we don't want to have edge effects. And so when you have a very small patch of space, all of your physics is dominated by the boundaries, basically. So the surface to volume ratio is very, very large. And so if you have solid walls, they're going to massively influence the outcome of your simulation. So the way to do this is to trick the system into thinking it's infinite. And so we basically tile space with our fundamental simulation cell. So you have your little nanoscopic box, and then you periodically replicate that box in all three dimensions. And so this is our fundamental cell here, and then we've replicated it by tiling it over all space. And so basically what this means is we have periodic walls. And so if you're an atom and you start to encounter the bottom wall here, you move out of this wall and into the next image of your fundamental box. In practice, what this means is that if you fall out of this wall, you re-enter through this wall. And so we're sort of tricking the system into thinking it's infinite. There are no walls in this system. If you fall out of the box, you just fall back in the other side. And so this is the way we try and convince the system it really is an infinite system. So of course, if our fundamental simulation cell is too small, we have all these artifacts from it being periodically replicated. So it needs to be big enough, but not too big that our computational cost is going to be too large. And so in lots of the things that you do, you typically try and compute the property of interest or predict the property of interest in a variety of box sizes, and then try and extrapolate that to infinity. And so that's what one of the standard tricks we do in molecular simulations. So one of the things you have to worry about when you have these infinite tilings of space is cutoff distances. And so I talked about earlier how one of the ways we can beat this n squared scaling of all the pairwise interactions is to specify a cutoff and say that, you know, if two atoms are further apart than this cutoff, I don't worry about what their interaction potential is because I think it's going to be screened out. So if you're in a periodic box, you need to make sure your cutoff distance is less than half the box length. If that is not true, you start to interact with multiple copies of your neighbor, and so you have horrible artifacts because you're seeing your neighbor on the right, you're also seeing her on the left and on the top and on the bottom, and so this causes a big mess for your simulation. It's very unphysical. And so if you try and set your cutoff too large, typically your simulation engine will throw you an error and tell you this is a problem, and this is where that error is coming from. And so there's some sort of trade-off to be done. You want your cutoff to be long enough so that you're not missing important parts of the force field, and that means your simulation box has got to be big enough, and that means you've got to have sufficient compute power to simulate that box. And so that's one of the things that restricts how long we can simulate in time. Okay, and so just to touch on a little bit of thermodynamics, just because I think it's important. I think it's useful to make the distinction between what we calculate in experiment from what we're calculating from simulations. So if you're doing an experiment, you're typically computing what's called an ensemble average. So if you've not heard this terminology, don't worry about it, but it means that you have Avogadro's number of atoms in your system, and so all of the quantities that you're calculating are going to be averaged out. So you can ask every atom what its velocity is, for example, and by taking an average over a large enough number of atoms, you have a very well-defined temperature. So your temperature is basically a delta function. So if you want to compute quantities in this way, it reduces to an ensemble average. It's very hard to do numerically, and so what we do in molecular simulation is actually take, instead of a very large patch of space in which you can sort of measure quantities in lots of different places and take an average, we simulate a very small patch of space, but just simulate it for a really long time. And we hope that those two averages are the same thing. And so this is sort of a time average. So an ensemble average, very large system. We're sort of getting our average spatially because we're measuring things over a large space and taking the average. A time average is taking a small patch, which is all we can really simulate it for a really long time and taking a time average. So that's an important distinction to make because it appeals to this thing called the ergodic hypothesis. And so this is really the cornerstone of all molecular simulations if we want to relate them to experiment. That we believe the time average we get from molecular simulation is the same as the ensemble average we get from experiment. So if that didn't make too much sense to you, don't worry about it, but it really just reduces to, we need to simulate sufficiently long in order to make a converged estimate for our property. If we simulate only a short amount of time, we don't really believe we're doing a good job of estimating something that's an equilibrium property. So that's why we need to simulate long enough, and why we want to do simulations on big computers like Blue Waters that allows us to simulate big patches of space for a really long amount of time. For slow processes that are sort of activated things, so sort of translocation through a membrane, maybe we will never see it in a molecular dynamics simulation. It will just take too long to see that event happen. And so we may need to use accelerated sampling techniques. And so we're not going to do any of these today, but I wanted to make you aware that they exist. And so if we want to simulate things that are longer than sort of microseconds, maybe the translocation of a protein through a membrane, or perhaps the spontaneous evolution of a dislocation at a particular stress in a metal, is a process that has a characteristic time scale of several tens of microseconds or longer. So molecular simulation will never allow us to see that. So you can think about that as a system being trapped behind a large energy barrier. So how can we convince the system to simulate that event? So you want to accelerate it, and there are a number of different ways of accelerating things. And so if we can post these slides, you can look these up later if that's something you're interested in. But I just wanted to make you aware that these things exist that allow you to simulate long time scale events. Okay, and so just to close this section, there are some specialized variants of MD beyond what we've discussed so far. So if you really think electronic effects are important, is there a way of actually incorporating them into your molecular simulation? Because we talked everything so far was classical mechanics. So yes, you can do so-called car-Parnello molecular dynamics. And so basically this is ab initio molecular dynamics. So what you do is you set up your system with all the nuclei and all the electrons. You use then some electronic structure calculation to compute all the forces, explicitly accounting for the electrons, and then you evolve your nuclei according to those forces. And so it's sort of a hybrid methodology where you actually don't need any classical force fields, such as the ones I showed you earlier, because you're doing everything from first principles. Problem is it's super, super slow. So if you want to simulate more than, say, a picosecond, you really can't do it with modern techniques. But in principle, this methodology exists. If you want to simulate chemical reactions, if you want to simulate bond formation or breaking, again, we don't have any electrons in classical molecular dynamics, and so it's a very difficult thing to do with a classical force field. If that's something that's important to you, you can use a fancy force field known as the REACTS-FF, the reaction force field, that allows you to sort of simulate in a sort of ad hoc fashion chemical bonds breaking and making, if that's something that's interesting to you. A lot of the molecular dynamics codes, LAMMPS included, have GPU support now, so you can exploit these graphics processing units with sort of these massive cores, massive numbers of cores in order to speed things up. And so any modern laptop will have a very fast video card in it, and you can actually sort of hijack that video card to do scientific computation for you seamlessly just by flicking a flag in the simulation code. And then we talked a little bit about implicit models, so implicit models for electric fields or for water or things like this. Okay, so before we move on to some limitations and then of molecular dynamics, so what I've told you so far, it sounds pretty great, but what can't it do? So there's no electrons, there's no chemical effects, but then we say there are some special force fields, no quantum effects, but some codes, GROMACS I know does it for sure. I don't know whether LAMMPS does it, I've not checked it out recently, but you can actually tell your simulation that you want to simulate everything classically except this tiny pocket of space, perhaps a few atoms in your system that you want to treat quantum mechanically. So for example, if you want to do ligand binding, you might simulate the active site or the docking site quantum mechanically because you want to worry about electronic effects, and then simulate the rest of your system classically. So that's a feature of many modern codes. How transferable your force field is. If you want to simulate something at sort of billions of gigapascals, probably your force field isn't going to work very well, so you need to be worried about the limitations of your force field. So under what conditions has it been validated and when does it break down? Time and length scale limitations, we can only really go to sort of nanoseconds, maybe microseconds, maybe milliseconds if you're David Shaw and you have a really fancy machine. So you need to pick the right tool for the job. So if you're interested in longer time scales, molecular dynamics is not going to be the one for you. And statistical significance of a single trajectory. So you get some time on blue waters, you set up one run, it goes for sort of a millisecond, that's great, but is that a statistically significant run? Was the trajectory you simulated sort of representative of what actually happens in reality? Or should you perhaps have done 10 shorter runs that you can then statistically average? So worrying about these things is important. And then of course equilibration. So have you simulated long enough, if you're interested in equilibrium phenomena, to actually be equilibrated? And that is the number one mistake in simulations. Your answers that you get from simulations are not meaningful because you've not simulated long enough. You're not attaining the equilibrium answer. So you compare to experiment, things are vastly different. You're not equilibrated is probably the answer. Maybe your force field isn't adequate, so garbage in, garbage out. It's pretty standard for numerical simulations. Delta T is too large, and so you become too greedy with your time step, and so you want to shorten that down to make sure you're conserving energy and your system is stable. System is too small, so this is what we alluded to earlier, that if you're computing a property, say the bulk modulus, you want to do it in a simulation cell that's this big, this big, this big, this big, and try and converge that to the infinite size limit to see your answers are meaningful. And then perhaps you just missed some important physics or chemistry. Maybe you didn't think about putting defects in your system or any impurities or ions. So being aware that your simulation is only going to be as good as how you set it up. And so you've got to get all the correct physics in there at the beginning. And then sort of a technical issue, your cutoffs are too short. So perhaps you've tried to speed your simulation up by having very short cutoffs, but you're sort of missing long range effects and your system is not behaving as it should. So just some common mistakes that we all make them when you start these things, and so just to be aware of. Okay, so that's all the theory. So I think it's worthwhile talking about that before we do the hands-on stuff, so it makes sense. And so now we're going to talk about the packages, and then we're actually going to get onto the hands-on side of things. So are there any questions on any of the topics that I raised so far? Okay, great. So let's talk about how we actually do these things. So, of course, the practice is a lot more fun and a lot more interesting than the theory, so hopefully we'll have some fun doing some simulations together. And the package that we're going to use is called LAMMPS. And so there are a bunch of different packages. There's GROMACS, CHARM, AMBER. Some of them are free, some of them are expensive. NAMD is developed here by the Schulten Group at the University of Illinois. It's a terrific biomolecular simulation package. LAMMPS is typically the right package to use if you want to do sort of solid state stuff, so crystals, metals, alloys. GROMACS, CHARM, AMBER, NAMD, D. Shaw's package, Desmond are all sort of geared for biomolecular stuff. And so that's why we're going to look at LAMMPS today. Okay, and so what do we use these things for? And so we can use them for things like fracture mechanics, and so maybe you want to start deforming your metal, and so you build a metal crystal, you apply some forces to it, and you watch how a crack propagates. That's a pretty standard application of LAMMPS. Maybe you want to look at sort of solid-liquid equilibrium, and so this is silicon crystallization. And so we took liquid silicon just above its melting temperature, and then we told the thermostat in our simulation to cool it down, and you can watch this thing crystallize. And so maybe that's useful if you want to see the impact of sort of impurities on crystallization, or if you have a brand new material and you want to make a prediction for its melting temperature, maybe that's something you can do using molecular dynamics. And then if you're interested in sort of biomaterials or sort of protein folding, I've got this sort of fun movie from the Pandey lab at Stanford, and so he's folding this millisecond folder known as NTL9. It's sort of a fun movie, so let's take a look at that. So basically they just download this protein from the protein data bank and they unfold it, and then they want to see how it's folding. And so you can see this simulation, the protein is folding. So I talked to him once, and so he made this movie, and he was showing it to his friends, and his friends said, well, this is great, but you know, this is a super dramatic thing. You need to make it more exciting. And so he got one of the guys in his lab to put this music behind it and post it on YouTube. So it's a very dramatic folding of a protein. So things are not looking good. We made it. So it's sort of fun, but what's really cool about this is they took the completely unfolded protein, and actually the prediction they made from molecular dynamics matches the experimental structure of the protein, which is terrific. Question?
So, do you have any idea what the order of magnitude is of the likelihood of transition out of the non-native state? Did you have to do any special guidance to get it to seek a rare state?
So I believe this is completely unbiased. So this is just evolving according to the laws of physics that they programmed in. And of course they had phenomenal computational horsepower. So they actually used this distributed folding at home code, which is sort of like, you may be familiar with SETI, this thing where you can use your screensaver to find aliens in the universe. And so Vijay Pandey wrote this folding at home, which uses screensaver cycles to actually fold proteins. And so he had massive computational horsepower, and so that allowed him to get here. And this took sort of milliseconds, and so this is not the sort of thing you can do on a laptop. You would need to use an accelerated technique to do that. And so if anyone's sort of a protein folding person, you can see sort of there's a nice alpha helix here and then the beta sheet on the other side, and so it's this nice folded state, and this is biologically active form. So some sort of fun stuff you can do with molecular dynamics. Okay, so let's move on to the hands-on portion. So the code we're going to be using is LAMMPS, and so it's supported by Sandia. It stands for Large-Scale Atomic Molecular Massively Parallel Simulator. So the things we're going to be doing today are sort of small, and so they're actually serial things, and so we're just going to use one core on our laptops for the illustration purposes. But this code scales extremely well to multi-cores, and so I think the scaling is like almost linear, and so it's terrific. And so if you have a lot of cores available to you, LAMMPS is a great package to use. And so this is the home page. It's sort of not the fanciest website, but it's very user friendly, and so you can download the code from here. A bunch of documentation, lots of nice user support, and they got a nice graphic there, which sort of diffuses apart if you hover your mouse over it. So it was born in the mid-90s as a cooperation sort of between academia and industry, and so Sandia, Lawrence Livermore, Cray, Bristol Myers Squibb, and DuPont. It's now hosted exclusively at Sandia under DOE funding. The current release is in C++ with MPI support. That's where it gets its parallelism from. I think it was originally written in Fortran, so thankfully we don't need to worry about that anymore. Everything's sort of nice, clean C++, and it's open source and free under the GNU license. So you can download immediately, and I think Neil provided you links for all these things to binaries that are immediately available for Linux, Mac, and Windows, or you can compile from source, which is actually pretty painless. It's sort of very nice. And there are various other ways you can get it. And it's free, and so this is terrific. So how do we actually use LAMMPS? So the first thing maybe to mention, there's no GUI, and so that can put a lot of people off. When I teach my class on this, people don't like the fact that there's no GUI, but it's actually super simple. Basically everything is an input script, and then you type one line into your terminal, which looks like this. So this is your executable, you're feeding it an input script, and then just everything happens on the terminal. There is some sort of user-submitted, user-contributed Python tools that allow you some limited visualization, but I recommend you just run it in its native form in the terminal. It's easy enough. And the input scripts are actually pretty straightforward, and so we're going to go through one in sort of gory detail in the first tutorial that we do, and then the second one we'll go through it a little quicker. But basically it's very simple the way that we set things up, and it's very intuitive. And so now you know a little bit about the theory. Each of these blocks will sort of make sense to you. Documentation, the manual's great. There's a web manual, and you can also download a PDF. There's a bunch of tutorials right on the website there, so I've just pulled this box from the LAMMPS homepage. There's a bunch of user support here, so sort of workshops, user scripts and how-tos, which are pretty nice. And the user base is pretty friendly, and there's a mailing list. And so if you're sort of really stuck with something, there's this forum that you can email sort of comment or a question to, and folks will typically reply pretty quickly. I should also mention there's really excellent third-party tutorials hosted by Mississippi State University at this link here. And the tutorials that we're doing today, when I was putting them together, I sort of looked back at how I learned LAMMPS, and it was through these tutorials, and so I adapted some of them for us today. So these are actually terrific, and in my opinion, they're better than the ones on the LAMMPS website. And so that might be a great place to start, beyond what we do today. Visualization, so LAMMPS has no GUI, it has no built-in visualization engine. The one we're going to use is Ovito, and I think Neil put that on the virtual machine. It's free, it's available from this link. I think it's just like one guy in Germany just wrote this thing and hosted it online for everyone to use, so it's terrific. It's a really nice clean package and available for all platforms, so you can get it from that link there. Okay, and so how do we run a simulation? And so we had that sort of flow diagram a number of slides ago. This is sort of an abbreviated version of that, sort of specialized to LAMMPS. And so on the left-hand side here is how you run things on your sort of local machine. On the right-hand side here is for sort of distributed computing servers. These are all for sort of PBS jobs. So let's just worry about the left-hand side. You need two things. You need your input script, which we're going to discuss, that tells LAMMPS how to set up the simulation. And you need your force field, which we're going to download from NIST, which tells the atoms how they talk to one another. And then, of course, you also need the LAMMPS executable, which you've built from source or you've downloaded the binaries. Then you run your simulation just by calling executable and feeding it the input file. And then it's going to dump a log file, and you can also tell it in the input script to dump so-called dump files that hold your trajectories, basically. It holds information about the atoms at every time step, which you can then subject to analysis offline. And the way you post-process is typically using things like MATLAB, Ovito, or VMD. And I think maybe tomorrow somebody's going to talk about VMD, which is Visual Molecular Dynamics, which is built here by the Schulten Group, the folks who make NAMD. Okay, so hands-on. And so this was adapted, like I said, from the Mississippi State stuff that was developed by a chap, Mark Chopp, who's now at the US Army Research Lab. So if you're interested in looking at more tutorials that are sort of like this, go to this link here. They're great. Okay, so everything we're going to do today, we're going to do two tutorials, and each one's going to look at aluminum. So I thought aluminum was sort of a nice, simple but non-trivial system to look at. It's sort of relevance for lots of sort of aerospace and auto industry stuff. And so I thought we'd do two things with this. The first one we're going to do is to compute the cohesive energy and the lattice parameter. And so this goes back to one of the questions, actually. So you set up your crystal, your atoms are too far apart. It turns out the lattice parameter was smaller than you anticipated. So can we get the molecular dynamics engine to compute that for us? And we're going to do that and also compute the cohesive energy, which is to say you take your crystal, you separate all your atoms to infinity, you measure their energy, so that's our zero baseline, you bring them all into the crystal, and the energy obviously drops because your potential energy is falling into a well. Can we measure that energy? And that's something that's experimentally accessible. So that's going to be tutorial 1. And in tutorial 2, we're actually going to take our equilibrated crystal at the correct lattice spacing and pull on it, and we're going to measure the Young's modulus. And so this is going to be an in silico prediction for the Young's modulus of aluminum, which is sort of one of the simplest, actually, predictive properties you can compute from molecular dynamics. Okay, so let's start with the cohesive energy. So we're going to take our aluminum. It lives in an FCC crystal, and so this is an illustration of a crystal here, and so these are the sort of corner atoms, and then the atom in the middle of the face there. And the lattice parameter, or the lattice spacing, usually goes by the variable A, which is sort of the side length right there. And we'd like to compute the cohesive energy, which is the energy of the solid minus the energy of the atoms at infinite separation. And we're going to take the energy of the atoms at infinite separation as our zero baseline of energy. So if we can measure the energy of the solid, then we've got our cohesive energy. So pretty simple calculation. Experimentally, we have the cohesive energy is negative 3.39 electrovolts per atom, and the lattice parameter is 4.0495. And so those are just drawn from these experimental references here. So what's our strategy? We're going to download an EAM potential for aluminum from the NIST repository, and then we're going to optimize the cohesive energy as a function of the lattice parameter. And so let's see how we're actually going to do that. Okay, and so if you want to direct your browser to this link, and so ctcms.nist.gov/potentials, and then scroll down a little bit, you're going to see this nice big periodic table. And so okay, and so I've gone to this link here. If you scroll down, you will see the periodic table, and you're going to click on aluminum, and you're going to see all the different EAM potentials that are available for aluminum. Okay, and so then if you go, the easiest way to do it is just if you Control F and find AL99, that's the beginning of the EAM potential we're going to download, and this is the guy that you want. So it's the al99.eam.alloy is the parameters that you want to grab. Thanks, Neil. So actually, if you're having problems with this, in the zip file that we're going to download in the next slide, I actually already pulled the EAM potential from the website. And so if you're having difficulty with this, there's another way to get it. Okay, and you should also worry about when you pull it down, well, my system at least appends .txt to the end of the file. If your system does that upon download, you want to delete that .txt. You want it just to have the file name al99.eam.alloy. Okay, has everyone got that okay? Anyone having problems? So the other way to get it is to download it from my website.
You have to have the www on it on the front of CTMS or whatever. It doesn't work.
If that's giving you headaches, I've packaged these input scripts together in this zip file, and actually that zip file also contains the EAM potential that we got on the last slide. So if you direct your browser to this link, which is just my personal web page where I've hosted this thing, you should be able to grab everything that you need to run the simulation, except for the executable. How are folks doing with that? Is that working? So it's not actually navigable. You just have to type this whole thing in. I think Neil may have also placed a link on the ICME at UIUC webpage. So under the agenda, under the LAMMPS thing, there's a link you can click to grab this. Yeah, sorry. So this is not navigable. You have to type in this whole thing.
Inside the virtual machine, it's going to make your life easier. Otherwise, you have to figure out how to transfer it from your external downloads over into the virtual machine.
Oh, I'm sorry.
So how are the various potentials that were listed on the website differ? I mean,
So they just come from different sources, and so if you are familiar enough to know the properties of one versus the other, some can be better at reproducing, say, Young's moduli, whereas some do a better job of reproducing, say, yield stress. There is different parameterizations. So the one we're using is sort of a vanilla, sort of generic potential. It works pretty well for everything. I think there is some, if you go to the webpage, there's some sort of verbiage around each one that tells you where it came from and the authors and things like that, so you can look up the scientific paper. Okay, so stick your hand up if you're still having problems with this, or if most folks got this.
Do you need the tar file to see this?
The tar file?
The tar one, the one with third file. Yeah.
This is, so these are going to come down with the zip file. This is the LAMMPS executable that you should have compiled on your machine or is within the virtual machine. If you've not got that yet, you can go to the, if you just Google Sandia LAMMPS, and you can download a binary for your machine pretty quickly. But I think Neil has hosted that on the virtual machine. Okay, so can I move on, or is anyone still struggling? Okay, so let's proceed. So let's open up the input file. And so al_fcc.in is going to be the input script that we're going to use to tell LAMMPS to set up and run our simulation. And so you can just open that in a text editor. So if you just grab that input file and drop it into TextEdit or whatever you use on your machine, it's just a text file that we're going to look at. So has everyone managed to open that up? Okay, so then let's run through the different blocks of this input file and ask, what are we doing? Okay, and so the top block is initializing the simulation. And so the first line says units metal, and so we have to tell LAMMPS what units we're operating in. And so we've chosen to operate in the metal units. And so these are the different quantities that we're operating in, the gauge of our simulation. There are various other ones. You can choose SI or whatever. But it turns out, I think for all the EAM and the MEAM potentials you need to be operating, that you download from NIST, you need to be operating units metal, or you're going to get junk results. Okay, so that's pretty easy. We're three-dimensional, so LAMMPS can do two-dimensional simulations also. You want to specify your boundary conditions, and so this boundary PPP means periodic in X, Y, and Z. You can also specify some of the boundaries to be non-periodic, if that's something you're interested in. And then the atom style is atomic, and so that's just saying how are we going to specify what our atoms look like. You can also specify your style to be, say, molecular, or there are various other things you can choose, but atomic is the usual one. Okay, so stick your hand up if there's any questions or you're having problems. Yeah.
The unit you said metal, then you have the explanation. Is that in the book, right?
It's in the book, yeah. So that's pulled out of the documentation.
So if you are using anything, just go back to the board and check it.
Precisely, that's right. So yeah, so I typically just have a PDF version of the manual on hand whenever I'm doing a simulation. I look up the lines I don't understand. The HTML one's pretty good because you can actually just navigate to any sort of line in this file. So if you're interested in boundary, you just go to the website, open up the HTML manual and look for boundary and click on it, and it tells you everything you could ever want to know about boundary conditions. Yeah, it's very well documented. Okay, so we've sort of initialized our simulation as sort of units, the dimensionality, periodicity of the box. Great. So now we actually want to populate it with some atoms. So far we just have an empty box. So we're going to create an FCC lattice, and we're going to specify a lattice spacing of 4 angstroms. And so we know already that that's the wrong lattice spacing, but we're pretending that we don't know our lattice spacing for aluminum. That's what we're trying to calculate. So we're going to see if LAMMPS can do that for us. We're defining a cuboidal box, and so the keyword is region. We're labeling it box, and it's going to be a block type region. You can also have things like cylinders or prisms or whatever, but we're just going to make a simple block, and we're going to make it of length 1 in X, in Y, and in Z. And the units are going to be in lattice. So 1 lattice spacing in X, 1 lattice spacing in Y, 1 lattice spacing in Z. So basically what we have is sort of the fundamental unit cell of an FCC lattice with a lattice spacing of 4 angstroms. That's what we've told LAMMPS we want it to make.
Can you come back to this later and talk about what other region shapes would do in the simulation?
Sure, yeah, that's something we can look at. And then we're going to create it with 1 atom type. And so we're going to create a box with 1 atom type in this region that we've called box. So we labeled this region box right here. So we're calling it again, and we're saying we're only going to have 1 atom type in it. If you have an alloy, you might have 2 or 3 or more atom types. Okay, so just stop me if anything is not clear. Okay, now we're going to actually build the crystal. And so we've told LAMMPS what's going to live in this region, but we've not actually built it yet. We've created the box, but we've not actually created the crystalline lattice. So let's do that. we're now going into this lattice we've created. So lattice FCC, lattice constant of 4, and we're specifying the orientations. So we want the x-axis to be the 100, we want the y-axis to be 010, and we want the z-axis to be 001. You can specify these to be whatever you want as long as they're orthogonal, so the different crystal lattice directions. So we're just keeping it simple right now. And then we're creating the atoms. So we're creating the atoms of type 1 within the box. Great, so we've now made our fundamental simulation cell. So this is one of the deficiencies of not having a GUI. You have to sort of keep all this in your head, but it's pretty simple, I think. Okay, now what we're doing is we're going to replicate this domain. So we're going to say we don't just want one fundamental simulation cell, we actually want 2 in every dimension. So we're making our fundamental simulation cell, which looks like this. And so it's going to have our atoms spaced on the FCC lattice. And then we're going to replicate it again in X. So it's going to live like this. We're actually going to have a second guy right here. And we're going to replicate it again in Z. And then we're going to replicate it again in Y. And so we're actually going to have 8 of these little boxes. Now on top of that, we've got the periodic boundary conditions. So these are the atoms we're actually simulating in LAMMPS. And then we've also told LAMMPS we want to be periodic. So if an atom falls out this side, it's going to come back in this side. Yeah?
So you have you have like region, box, block, and then you said it's 1 unit lattice in each direction, and then you repeat almost the same command. So my question is like the region SCC for, and then you define the orientation, X is 1, 0, 0, and Y is 0. This seems like like it's redundant. You know what I mean? Is there a way like we just have that maybe one statement instead of lattice FCC4? Because we're saying that this is FCC with 4 angstrom. These are the orientations.
That's right. So the question is this line redundant with this line? And the answer is yes. And so I think we could just call the second line and we'd be fine. The reason we call this first is that we actually then want to build a box around it. So we just want to make sure the box is the right dimensions to fit the lattice. But I think probably if you eliminate that line, you would probably be fine. You could try and see. Okay, so we've told LAMMPS our initial crystal geometry. So it looks sort of like this. So now we need to tell it the potential. So again, going back to these ingredients, we have our initial positions. We've not given the velocities yet. We're going to do that in a second. But now we need the interaction potential. So that's the recipe we're following. So defining the interaction potential. Oh, I should have also mentioned that whenever you see a line starting with a hash, it means it's a comment. And so that's a nice way of arranging your file so it's sort of humanly interpretable. So we're divided into these blocks here. Okay, so we're defining the pair style. And so here you might have Lennard-Jones, you might have Coulombic. The one that we're going to use is the EAM potential for an alloy. That's the form of the potential we're using. That's the one that we downloaded. We know that because it ends in .eam.alloy. And so we're telling LAMMPS that you should expect an EAM alloy potential. We then tell it to import the potential. And so we say pair coefficients. So this is a little bit of a misnomer because EAM is not strictly pairwise decomposable. It's actually n-body, but it's okay. And so we're telling it that we want to import this file, which is going to contain all the things that our EAM potential needs. So it's going to have this embedding function, the density function, the pairwise interaction potential. That's all encoded in that file we downloaded from NIST. And we're telling it that that's what we want you to use for the interactions between pairs of atoms. And so we have 2 asterisks here, which means that we're going to use those parameters for all types of atoms in our system, so all possible types of pairwise interactions. Because we only have 1 atom type, we could have also replaced that with 1, 1. That would have been a fine thing to do. Okay. Sorry, is there a question? Okay, and so then we want to specify a couple more things about the force field. We want to specify the neighbor list, and so the force field has built into it a particular cutoff distance, and it says if 2 atoms are separated beyond this cutoff, we don't need to worry about their interaction. And so it turns out that there's an efficient way of not recomputing the neighbors of every single atom on every single time step, which is to have a sort of skin. And so imagine your atom 1 here. You're living in a crystal with a bunch of other atoms who may be moving around. And so if you're radius of interaction looks like this, and so the potential, your EAM potential, tells you need to talk to everybody who lives inside this radius. Maybe you don't want every time step to go and ask all your neighbors, are they close enough to interact with you? Maybe you don't want to ask that every single time step because it's inefficient. So what we typically do is a little trick, which is to every few time steps rebuild a neighbor list at a slightly bigger distance. So say every 10 time steps we rebuild our neighbor list for this atom. And then we don't have to worry about doing that every time step, provided no atom sort of traverses the skin thickness in that amount of time. So that's the trick that we're using here. So we're telling it that we want our skin thickness to be 2 angstroms. And we want to use binning to compute our neighbors. That's just the way you compute your neighbor list. And then we're saying, I don't want you to compute every time step. I want you to compute your neighbor list every 10 time steps. But I do want you to check every time step that no atom has moved the skin thickness. Because if an atom has moved the skin thickness, then you could have violated your neighbor list and you actually need to recompute it. So LAMMPS is clever enough to do both things. We're getting a performance boost by only computing our neighbor list every 10 time steps, but it does this quick calculation, which is actually sort of negligible cost, to compute whether any atom has sort of had the possibility of traversing the skin thickness. And if it has, it does an on-demand neighbor rebuild. So that's what's happening there. Is that sort of clear? So it's just a technical trick. So molecular dynamics, the theory is super simple. It's F equals ma. All the difficult stuff is just all the technical implementation. Okay. So then we're defining a couple of things called computes. And so LAMMPS has 2 user-defined quantities that you can, they're not quite user-defined, but they're built-ins that you can call, called computes and variables. So keyword compute, we can define this quantity that's recomputed every time step. And so every time you update your positions and your velocities, you tell LAMMPS to recompute this quantity. So this is something that's interesting to you for whatever reason. So this is compute something called ENG. We're defining this name, so we can give this whatever name we want. We're calling it ENG for energy. It's defined over all atoms, and it's the potential energy per atom. And so every time step, LAMMPS goes in and asks every atom what its potential energy is, and stores it in this big vector called ENG. We're defining a second thing called E-atoms, which is basically taking this vector of energies and adding them all together. And so it's the total system potential energy. So the way it's calling this is to actually compute this thing E-atoms by doing a reduce sum operation on this vector. So it's taking this vector, adding all the elements together. We could have calculated it directly, actually by making a different call, by saying compute E-atoms all PE. That's a simpler way of calling it. It's saying define this compute called E-atoms, which is just the potential energy of everybody in the system. So super simple. And the way that you reference a compute that you've established is through this C underscore. So you define a compute in the following manner: compute the name you want to give it. When you then call it later, you need to have a C underscore and then the name that you gave it. And so in the second line here, you can see that we're referencing this compute as C underscore ENG. So it's just a convention for LAMMPS. It's sort of slightly inelegant, but it works. So we'll come to variables later. Okay, then we said when LAMMPS has finished executing, it produces 2 things. It produces a log file, which is basically what it prints to the terminal. It also dumps to a log file, so you can go back and see exactly what it did. And you can also ask it to dump output in particular formats. So in this case, we're going to ask it to dump basically the trajectory of all the atoms. And so this dump thing is the keyword. So dump, we're going to give it a tag, number 1. It's going to be all atoms in the system. The form we want it to dump in is in atoms, and we're going to call it dump.relax, and we're going to dump every single time step. So dump, this is the tag we're giving it, number 1. It's going to be over all things in the system. The thing it's actually going to dump is atom, which means the atomic coordinates. It's going to happen every single time step, and it's got the name dump.relax. So this is basically our trajectory file. It's the coordinates of every single atom at every single time step, which we might want to analyze later. And so the format is going to be something like this. And so you can open the dump file in the text editor later, and you can see that it looks like that. Okay, we okay so far? Okay, so what are we actually going to calculate? So we're not actually going to do molecular dynamics this time. We're going to do a minimization. And so we're going to take our potential function and we're going to minimize it. So why do we want to do that? Well, we want to find the equilibrium lattice spacing In the next tutorial, we're actually going to do molecular dynamics. This one, we're actually going to find the equilibrium lattice spacing and the associated cohesive energy. And so what do we want LAMMPS to do? So run minimization. We're going to reset the time step to 0. So that's fine. Every time you do a different part of your run, maybe you want to reset the time step, you can reset it to whatever you want. 0 makes sense. And then we're going to define this thing called a fix. So keyword fix. You can look that up in the manual. So fix is an operation that's applied at every single time step. And so the most common fixes are thermostats and barostats. And so the fix that we're going to apply is basically a barostat. And so we're going to fix, we're going to tag it with ID 1. It's going to occur over all atoms. The actual fix we want to call is box/relax. You can look that up in the manual. Basically, it's relaxing the pressure of the box. It's going to be isotropic, and we're going to put some maximum tolerance on it to stop it from exploding if we pick a really bad initial lattice spacing. So what this is going to do is it's going to, at every time step, after we update our positions and our velocities, it's compute the isotropic pressure on the box, and it's going to change the box volume if the pressure is away from 0. So if you're at too high pressure, the box is going to get a little bit bigger. If you're at too low pressure, the box is going to get a little bit smaller. And we've got this sort of threshold on it to make sure that if we pick a lattice spacing of, say, 0.001 angstroms, the thing isn't going to explode on the first time step of the minimization. Okay, we're going to see other fixes later. And there's another important variable called thermo, which basically is outputting your thermodynamic information to the screen. And so we can watch the log file either on the screen or in the text file that it dumps, sort of go through the simulation and see what's happening. And so this provides sort of instrumentation for the simulation. You can ask LAMMPS to output the pressure, the temperature, the kinetic energy, the potential energy, so you can follow sort of what's happening in your system, whether you're exploding or whether you're sort of nicely equilibrating to the temperature that you want, or whether your minimization is converged to a potential energy minimum. So we're seeing thermo 10, meaning we want you to output to the screen every 10 steps, and we want our thermo style to be custom. So usually I use a custom thermo call because I want to output different things depending on the simulation that I want. And there are various keywords you can look up in the manual as to what you can actually output. So here I'm asking LAMMPS to output the step number, the potential energy, the box side lengths in the X, Y, and Z directions, the pressure, and the 3 diagonal components of the pressure tensor, and then this compute that I defined earlier, E atoms, so the total potential energy of all the atoms. And so I think this one should actually be the same as PE. Okay, so that's sort of our instrumentation block. That's what we want LAMMPS to tell us every 10 time steps. And now what are we actually going to do? We want to do a minimization. So this call is minimize. And so we're doing a minimization style, conjugate gradient. So you could also do steepest descent. In the next tutorial, we're not going to do minimization. We're going to do molecular dynamics. So we wouldn't call minimize. We'd actually call run, which means do molecular dynamics. But here we're doing a minimization. And how do we want to minimize? We want to minimize particular tolerances. So 1 part in 25 in the energy, 1 part in 10 to the 25 in the force, and put some maximum threshold in the number of iterations, so we don't just run forever. And so what we're doing is we're setting up our cell with a guess of the lattice spacing of 4, and we're allowing the simulation to relax, where the pressure is relaxing along with the simulation until we find our nice minimum in the lattice spacing. Question?
Yeah. What would
So in here there's no concept of temperature because all we're doing is a minimization of potential energy. So all we're doing is looking at the energy of our system and we're doing a conjugate gradient descent down to the minimum in our potential energy. So there's actually no kinetic energy, no sort of atomic motions in this system. Basically what we're doing is we're trying to find the equilibrium lattice spacing, then the next run we're actually going to allow things to evolve using molecular dynamics. Good question. Okay, and so this is where all the action happens. So this is the actual LAMMPS run, the minimization run. So just one line in our input file. And so we're going to see when we call that, we're going to get a bunch of stuff is going to get spat out by LAMMPS. Now, what are we actually trying to calculate? So variables are formulas that are evaluated when they're called. And so they're like computes, but they're not computed every single time step. They're only computed when we call them. So that's what distinguishes them from a compute. And so they're much more sort of simulation efficient because they're not happening all the time. And so what variables do we want? we're asking at the end of the simulation, I would like you to define the following variables for me. The number of atoms, which is just counting the number of atoms. This is a call you can look up in the manual. The total energy, which is the terminal value of our potential energy compute that we defined. The lattice parameter, and so that's the box side length divided by 2. Why is it divided by 2? Because we replicated our fundamental simulation cell twice in every dimension. So this is Lx, this is A. And so that's why that's 1/2 of Lx. And the cohesive energy is the total potential energy. So this is the variable we defined right here. When you dereference a variable, you have V underscore, so that's where that V underscore is coming from. And we divide that by the number of atoms, which we computed in this variable right here, to give us our cohesive energy, which is the other thing we wanted to calculate. Okay, so is that clear? That's sort of, we did our simulation, now we actually want to ask it a question. These are the questions that we're asking it. So did we compute something useful? Okay, so LAMMPS knows the answer. We'd like now LAMMPS to tell us the answer, so we need to print to screen. So the print call just takes the text strings, and then you use this $ brackets to print the value of these various quantities, these variables that we've defined. So we're asking LAMMPS, please print to screen the total energy, which is living within this variable TENG, which we defined right here, number of atoms, lattice constant, cohesive energy, and tell us that you're done. Okay, so that's the input file. So we went through that in a lot of detail. Well, hopefully you can see how the theory that we talked about actually translates into how we actually set up a simulation. And we'll see that again when we actually do the proper ND next time. This is just a nice entry level sort of example. So are there any questions about any of the parameters here? Really, LAMMPS is best learned by doing, and so do it, change the parameters, screw things up. Look up the manual, see where you went wrong. What other fancy things can you put into this input script to compute different things? Define your own variables, define your own computes. That's going to be the best way to learn these things. Okay, so let's run it. So the way you run it is very simple. So you just go to your terminal. Okay, so I'm in my terminal here. You can see if I hit LS, I've got my EAM potential. I've got my input script, and I've got my executable. So let's run this. So it ran very quickly. So this is the output the LAMMPS produced.
Is that working on LAMMPS? So you're at the LMP underscore back.
Right, so that's my executable. I don't know what the...
It's LAMMPS.
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 Okay. So your executable is going to look like LAMMPS, and then you just provide the input file through a less than. So folks managed to get that to run? So it's going to be ./LAMMPS. You don't need ./. Oh, it's a Windows machine. Okay, so you're just going to be LAMMPS.
Just type LAMMPS, LAMMPS, and then the caret, ALMPS.
Okay, so in your terminal it should be LAMMPS. Okay, do folks get that to go? Okay, let's give it a couple more minutes.
So where is your, what did you download? Did you download
The source file, yeah, it is. This is the plan correct.
Yeah.
There's no such file directly. I type this. Is there anything wrong with it? Is that right?
So hit LS. Yeah. Okay, so you're not in the right directory. So where did you download all this stuff to?
The download folder.
Okay.
Oh, probably, yeah.
Yeah, so if you navigate to the correct location, you should be good.
I don't know if
What does this do?
We should have seen what the note.
In what? If you just run the procedure here.
Yeah, so I know. This is
If you just run this file name, cause the
Anyone else having problems?
I have a question.
Yeah.
What was the reason for setting a fix of pressure of ISO?
So we want to equilibrate, we want to minimize our potential energy at 0 atmospheres.
Okay.
And so if we hadn't set that fix, the pressure could have been undefined or some crazy pressure. So we want to make sure that the equilibrium lattice spacing we define is at 0 atmospheres.
Zero external pressure.
Exactly, precisely.
And then here, after running the program, it shows some PXX, PYY, and PZZ.
No.
What are these things?
So those are the diagonal components of the pressure tensor. So the pressure in the x direction, y direction, and z direction. So those should all be the same because we've defined isotropic pressure coupling.
Okay.
You could define anisotropic pressure coupling for whatever reason you might want. If you had an anisotropic system and you could just allow pressure to relax along the z-axis, for example. Sometimes people do that in membrane simulations or things like that. Yeah.
When you mean the pressure in the direction, you mean the difference pressure between, for example?
So the pressure tensor is a function of the entire system. So you compute the pressure tensor over the full system, and then you can see if there's any anisotropy in that. So if there's a net pressure pushing in x and y or in z. Yep. Everyone else doing okay? Any more problems?
You're doing it LS, that's right.
You guys got that to run okay? Yeah.
I get an error that it cannot open the EM potential file.
Okay, so hit LS. So is that?
It's there.
You afraid?
Yeah. So that's you have the AL03. So you could do one of two things. You could re-download AL99, or you could change the call in your input file to be AL03.
Right. Oh yeah. I think I'm the wrong host.
Okay.
This is always the most exciting.
That's right. It's where the real learning happens. Are you folks, everything okay?
Yes.
All right, terrific. Okay. Everybody okay?
I know how to use it.
Okay, terrific.
But I got a few pointers when you talk. So.
Oh, I'm glad. Okay.
So did you say that you can't do a modifier Excel or LAMMPS? Is that what you said?
No, you can. You can.
Okay.
Yep, it's possible.
Because I was going to say it. I know how to do it.
Right. You folks okay back here? Everyone got that running? Okay.
I'm cheating, looking over his shoulder.
Oh, okay. That's the easiest way to do it.
For the input file, you didn't give it a path for the auxiliary file.
Okay, so I think most folks managed to get that to run. So let's take a look at the output. And so the output is in two places. So it's on the terminal, and it's also in the log file that came out. And so if you hit LS, or you just look in your window, you should see that there's some log file that exists in your directory. So you can just open that in a text editor, and so that's a written record of what LAMMPS actually did. And so let's take a look at what actually happened. So up at the top here, you can see the first block of code the LAMMPS executed was to build the system. And so we can see they're actually on a 1 by 1 by 1 MPI processor grid, which is to say that we're a serial code. And so we're doing serial stuff because we're doing it on our laptops today, but that's always there because LAMMPS is really designed for very large simulations. And so you can see how many MPI calls that you're using there. Okay, so then we're building the system, you're replicating your atoms. You can then see the actual run, and so we've built the system, we've told it the force fields, and then the thermal output that we asked for is now on our screens. And so we asked for the step, and so step 0, step 10, step 14, the potential energy, which is the same as actually the potential energy we defined through that compute. So that's good, those things match. And then the box sizes, the total pressure, and then the diagonal components of the pressure tensor. And so in this particular simulation, we're doing isotropic pressure coupling, and so those guys are all the same. You could do anisotropic pressure coupling, where you could allow the x direction to relax independently of the y or the z. Sometimes people do that for anisotropic systems like membrane simulations, or if you have some fancy cell that you're working with. Right now, we're just going pretty simple, and so those are all the same. Okay, so we see that we did 14 steps, and then we stopped because we hit our minimization stopping criteria. And so it says the line search alpha 0, which basically means that there's no change in the energy with the change in the position, and so that we've hit the potential energy minimum using this conjugate gradient search. Okay, so that's the termination of our simulation. Recall, it's not molecular dynamics. We're doing minimization right now. We're going to do molecular dynamics in a second. Then we do some CPU accounting. So LAMMPS always likes to tell you how efficient it was because how wonderful this code is. So it tells you how quickly it ran. Then some atom accounting. One thing that you might want to look out for here is right down at the bottom. You can sometimes see this line, dangerous builds equals 0 is not equal to 0. If that is the case, it means that, okay, I've erased this picture. It means that between neighbor builds, an atom could have moved through the skin thickness. So your calculations may be slightly off because you've not properly accounted for all your neighbors. So if you see dangerous builds, usually it's okay because it's not such a big deal. It gets averaged out in the long run. But if you see lots of dangerous builds, probably you want to worry about it. I always like to have this equal to 0, which means you're doing a proper accounting of all the pairwise interactions. Okay, then we asked LAMMPS to print some things for us. We asked it to print the total energy and number of atoms, and then what I've highlighted here, which is why we did this simulation in the first place, which was the lattice constant in angstroms and the cohesive energy in electron volts per atom. And so, depending on how you ran your simulation, you should probably get very similar answers to me, which was 4.05. Very close to experiment, 4.0495 for the lattice constant in angstroms, and the cohesive energy negative 3.36, which is very close to the experimental value of negative 3.39. So we can all pat ourselves on the back and say what a wonderful job we did with molecular dynamics. But really, we should be shocked if these quantities did not agree. If they did not agree, it means our force field is terrible. And so the AL99 is a good force field, it does a nice job, and so it's good that those things agree. So of course this is a tutorial, it's a toy example, but one could think about if you discovered this brand new material, you know, a high temperature semiconductor is going to make you billions and billions of dollars, and you want to simulate it. Maybe you do some quantum mechanical calculations, you build a new force field, a brand new EM potential that's never existed before, and you want to check that it's in line with the experiment. This might be one way of doing it, and if these things are off, that then gives you a route to start adjusting the parameters in your potential to reproduce reality. So sort of a toy example, but you know, this is the way that potentials are fitted at the end of the day. So people who are designing EM potentials are doing things like this and checking these things agree. Okay, and so that's sort of the question there. If we're studying a new material with experimentally unknown cohesive energy and lattice spacing, this is sort of where I'm trying to make a bridge to integrated computational materials engineering. That perhaps what we could do is do some electronic structure calculations down at this very low level here and bridge the cohesive energy and the lattice spacing we calculate from, for example, DFT, to help parameterize a new EM potential we could then use in molecular simulation. So why would we want to do that? If we can calculate things at the electronic level, why should we worry about making a classical potential? Well, perhaps you want to go to longer time and length scales. So you want to simulate things for, you know, microseconds over nanometers. DFT is not going to get you there, but perhaps DFT can give you a good classical approximation for a force field that can get you there. So the ICME is this whole idea of bridging, going from electronic level to atomistic level, perhaps up to sort of finite element calculations on the mesoscale, up to sort of macroscopic properties. So this example is drawn from someone who's studying reinforced titanium armor, going from calculations down at this level all the way up. Okay, and so that's your first experience with LAMMPS, so doing an energy minimization. So are there any questions about anything that we did there? Okay, so let's do molecular dynamics. So that's what you came here today to do. So, first of all, let's look at visualization. So the visualization here is not terribly exciting, but it's very straightforward. So I just have a little video here, which I'll start and stop, about how to visualize in Ovito. So I'm opening up Ovito. So you should have that in your virtual machine. So the Ovito window looks like this. So you've sort of got these 4 panes that automatically come up, and then the control pane is in the right hand side there. So what I'm going to do is go up to the File menu, I'm going to open a local file. So that's the option there, open local file. So hit that because it's a file on your machine. You're going to go to where you ran your LAMMPS simulation, and you're going to open up this relax file. So we asked LAMMPS to dump the atomic coordinates every time step. So it's dumped it into this file for us. And Ovito plays well with this file format. It's going to immediately recognize it. So you just click on that, click open, and the atomic coordinates spring into Ovito. So Ovito, by default, immediately expects just one frame of a movie. And so what you need to do is go down to this bottom right here and tell Ovito that this contains multiple time steps. So you just check that box. So it's going to happen right now. So now Ovito recognizes that this file contains multiple frames. And along the bottom of your Ovito window, you'll now see a slider with 14 frames in it. So my energy minimization took 14 steps, and I have one configuration of atoms for every step. Okay, so you see the different projections in these three panels here, and then the perspective view down here. And these are all sort of draggable. And so if you click your mouse on one of these panes, you can rotate or zoom and things like this. Okay, so then you hit play, and you can watch the simulation relax. And so you can see that the box size is changing as we relax from our guess of an initial lattice spacing of 4 angstroms to the final value, which we saw to be 4.05. So the simulation cell got a little bit bigger there. And so you can see here that we have our 8 copies of the fundamental simulations, fundamental lattice, FCC lattice. So this is number 1 down here, and then we replicated that twice in every dimension. So we could have run this simulation just with 1. So instead of doing replicate 2, 2, 2, we could have just done replicate 1, 1, 1, or omitted that line completely, because this is a trivially periodic system. When you're looking for things where you actually need to worry about atoms moving with different temperatures or dislocations or defects, you need to simulate bigger chunks of space, which is what we're going to do now. Okay, so did everybody get Ovito to run correctly? That was okay? So it can do some fancier things. We're going to do that in a second. VMD is also a nice option, so I believe VMD can also play well with LAMMPS. If you have that installed, you're welcome to try that on your LAMMPS output. Okay, so any questions about this sort of introduction? Okay, so let's actually do some MD. So tutorial number 2. So Young's modulus of aluminum. So this is sort of a perhaps more realistic and more useful calculation one might want to do. Okay, are we meant to do MD? Yes, let's do some MD right now. So we now know our lattice spacing, so we can now set up a nice equilibrated aluminum lattice, and then we're going to tug on it and watch how the stress-strain response occurs and compute a Young's modulus. This is actually a very useful thing to do. And so if you have a nice new material, and you have a nice new force field, you can make a prediction for the Young's modulus. So for folks that maybe are not materials engineers, the Young's modulus is the slope of this line, where this line is the strain in the x-axis. So this is the a dimensionless quantity which says how my percentage elongation, basically. So I start at a particular size, and maybe I tug on it to apply a force, and I make the material longer and longer. And this is the stress evolved responding to that strain. And so you can think about it 2 ways. You can strain your material and measure the stress, or perhaps you can apply a stress and measure how much you elongate. So either way is fine. You get the same curve. And the Young's modulus is the slope of this curve, which is basically the stress divided by the strain. And so if you're a very ductile material, you'll have a very low slope. You're very easy to stretch, like a nice rubber. Or if you're a very stiff material, like a metal, perhaps you have a steeper slope. You have a steeper Young's modulus. And of course, this has units of pressure, because stress is measured in pressure and strain is dimensionless. And so it turns out for aluminum, the Young's modulus is 69 gigapascals. And so, again, we know the answer. This is a sort of toy tutorial. How good can LAMMPS predict this value? So what we're going to do is we're going to set up an FCC aluminum crystal, apply an extensional force to pull it apart, and just plot this curve, basically. And then we're going to take the slope of the curve, and that's going to give us our Young's modulus. Sound good? Okay. Okay, so we're going to download the potential. We have that, so we can skip that step. We don't need to do that again. If you want, you could download a different potential and play with it, but we're just going to use the same one, so the L99. You've already downloaded the zip file, so you will have these other files that came down with the zip file that we're now going to use. So we'll have our input script, which is al_tensile.in, and in the next few slides we're going to look through that script and see what differently we're doing this time when we actually do molecular dynamics. We have our in potential, which already came down, and you have your executable. And then I've also put in here a couple of MATLAB M files that are going to do some nice post-processing of the LAMMPS output for us in an automated way. So we're actually going to watch the approach to equilibrium, so how the temperature and the pressure and the potential energy all equilibrate. And then we believe we have a nice equilibrated crystal of aluminum in an FCC lattice. And then the second simulation we're going to do is we're going to tug on it. And then we're actually going to have MATLAB plot the stress strain curve and compute the Young's modulus. So that's sort of the prescription. So let's do it. So let's take a look at al_tensile.in. So I'm not going to go through this file in quite as gory detail. It's very, very similar to the one that we saw before. And so I'm just going to show you the highlights. So, okay, initializing, we've got our units, our dimensions, our boundary conditions, etc. Here we've defined a variable right up top called lat_param. And this is our input from our last simulation. So we found out the equilibrium lattice parameter was 4.05 angstroms. So we're now dialing that into this script. And so we're going to immediately generate an FCC aluminum crystal with the right lattice constant. We're then going to use that variable at different points throughout the script, namely here and here, in order to generate our lattice. This is a nice efficient way of defining a variable once and then using the variable later in the script. So a very useful thing to be able to do. You can now use the script for different metals. So if you have another FCC metal with a different lattice spacing, the script is immediately transposable to that just by changing this single line up here. It's a very nice thing to do. Okay, so we're going to pull in our force fields in this block here, and then we're going to define some computes. And so the computes we're going to define for this simulation are slightly different. We're going to have our old friend, the energy, which is the potential energy per atom. But we've got this new guy that we've called CSIM. This is a compute called CSIM, defined over all atoms, and it's going to call the compute, you can look up the LAMMPS documentation for this, centro/atom, which is a central symmetry parameter for every atom in your simulation, based on an FCC crystal. So what the heck is this? So this is asking sort of how close to an FCC am I? So every atom computes this parameter and says how close to FCC am I? If you're interested in the mathematics, basically it takes every pair of atoms around it and tries to minimize this quantity CS, which is a central symmetry parameter. So for instance, if you're in a perfect FCC crystal, you take your distance to the atom above you and the distance to the atom below you, you subtract those two things or add them together vectorially as we're showing here, and you'll get a 0 if they're perfectly spaced in the FCC crystal. Similarly, all your other pairs of symmetric neighbors. If you're in an environment where your top neighbor is missing due to a defect or perhaps a free surface, this central symmetry parameter will go away from 0. And so how far away this guy is from 0 tells you how far away from an FCC environment you are. So it's not perfect, it doesn't tell you precisely sort of anything super physical, but it can give you a good idea of sort of the idea of how close to an FCC you are. If you're near a dislocation core, it's about 1, a stacking fault, you're about 5, a free surface, you're 23. And we're going to ultimately use this in visualizations in Ovito, and we're going to see the generation of stacking faults, dislocations as you pull hard enough on your aluminum crystal. And the central symmetry parameter along the dislocation is going to jump. Okay, so a common thing we do in materials science is compute this central symmetry parameter. So scrolling down a little bit in the input script, we actually have 2 molecular dynamics runs we're doing back to back. The first one we're going to do is equilibration. So we're going to reset the timer. We're going to specify our time step. So one of the questions earlier was how do you know your time step? It's 1 femtosecond. We can actually set it to 2 femtoseconds. Anything above 4 is getting a bit dicey. The way you check it is by looking at your energy drift over the long run, and if that's going crazy, you know you've taken too big a time step. The rule of thumb, 2 femtoseconds, 1 femtosecond, that's fine. We're generating our initial velocities. So this is called velocity. You can again look this up in the documentation. It's pulling the velocities from a Maxwell-Boltzmann distribution, just like we said in the theoretical things. We don't want to thermally shock our system. So let's start the velocities close to 300 Kelvin. So create velocities on all atoms at 300 K using this random seed. Based on just linear momentum, we're going to 0 to 0, place to 0. We don't want to worry about rotational momentum. It's going to be taken care of. So you can look at the various options there, but basically this is a Maxwell-Boltzmann call. Okay, so now we're going to fix our temperature and our pressure. So this is where these advanced techniques of not just doing F equals ma, but coupling to a heat bath and a pressure bath come in. So it's just a one-liner. LAMMPS is very efficient in the way we do this. We specify a fix. We label it 1. It's going to apply to all atoms. The fix that we're going to call is NPT, because we want to operate in the NPT ensemble. Fixed number of atoms, fixed pressure, fixed temperature. The temperature we want is 300 Kelvin. This is the start temperature, this is the stop temperature, and this is the drag coefficient on the thermostat that we're using. So 1 is typically a nice coefficient to use. And then we want isotropic pressure coupling. Start pressure is 0, stop pressure is 0. Again, the sort of time constant is 1. And then the drag you can impose to sort of even out the fluctuations. And so basically this is Kelvin, picoseconds. It's the time constant for the coupling. And this is in bar, picoseconds, and then this is a dimensionless parameter. You can look up the LAMMPS documentation if you're interested. But in just a nice one-liner, we've coupled to a thermostat and a barostat, and it turns out the default ones that we use are Nosei-Hoover thermostat and a Parnell-Raman barostat. So it's all embedded in there. So lots of complex math, nice algorithm, all in that just one line that calls a fix. Okay, so then we're going to do some instrumentation and output. So we're going to define a bunch of variables that we want to actually print to an ancillary file. So we have our log file, we're going to define a dump file in a second. I'm actually also defining a text file that we're going to import into MATLAB after the run is done. And in this text file, I'm going to have a bunch of columns. The first column is going to be the time. The next 3 columns are going to be the x, y, z dimensions of the box. Then it's going to be the box volume, box pressure, potential energy, kinetic energy, total energy, and the temperature. And I'm going to dump that every 250 steps to this file al_eq.txt, and I don't want it to dump to the screen because the thermo stuff is going to dump to the screen, so I don't want to interleave those two things. So you can define this to be essentially whatever you want. These different calls available are listed in the documentation, so you can see exactly what variables you can call. Okay, then there's the thermo stuff. We're going to print this every 500 steps. Custom thermo again with step, time, CPU time that's been used so far. An estimate of the remaining CPU time just based on an extrapolation. So this can be useful, which tells you whether you have time to go for a cup of coffee or go for a beer or go home and have a sleep. And so that can be a useful thing to have in your thermo. Then again, the box dimensions, pressure, potential energy, and temperature, because I don't want to see how nicely I'm approaching equilibrium. Then we have the dump, and so this is going to be the dump of all the atom coordinates every 250 time steps to this file I'm going to call dump.eq.lampstraj, and then we're going to do the run. So this is the place where we call the Verlet algorithm. So we're doing 12,000 steps off the Verlet algorithm off the system that we just set up. So it's going to be F equals MA plus a thermostat and a barostat, and we're going to periodically dump this output file and periodically dump this atom coordinates file and periodically write to the screen. Yeah, question?
So just a question about the, we're trying to calculate the numbers fine. So we want to, yes, find pressure and see what the expansion is like.
So that's just what I was going to say next. So we're not doing that yet. Right now we're just equilibrating our crystal to 300 Kelvin and 0 bar. So this is the first of 2 simulations that we're going to do. So we're going to know we're equilibrated when we plot this file using MATLAB, the pressure, the temperature, and the potential energy have all plateaued. Then we're happy we have a nice equilibrated crystal that we can then deform to compute the Young's modulus. So that's the protocol here. Okay, then at the very end, what we're going to do is clear our fix, clear our dump, and then compute some output. And so we're going to compute our terminal box dimension, the Lx dimension, because we're doing isotropic pressure coupling. It's the same in all dimensions, which we're going to use for our strain calculation later. So I should mention that's 4 o'clock. So if folks want to leave, I will post all these slides, but I'm willing to stick around until we finish this thing. So it's up to you guys. So I'll be here for as long as you want to be here. Okay, so that's the equilibration, and it turns out, and I know in advance, that 12,000 time steps is enough. So then right below that we've got a deformation simulation. So here's where we're actually doing the stress strain business. And so this is just scrolling down in the input file. So we're going to reset our timer, reset our time step, which is actually the same as before, so this is redundant. We're going to keep the same thermostat and barostat, but now we're actually going to do our stress strain calculation. So in this line here is how we apply the non-equilibrium straining. We're defining a strain rate. So the units of metal are in per second, so we're turning that into picoseconds right here. And then we're defining the strain rate is equal to this call up here divided by this to get it into the metal units, which are in picoseconds. We're then applying this other fancy fix. And so this fix here was controlling our temperature and pressure. This fix here is deforming the box. And so what this is saying is we're tagging it with the ID number 2. It's going to apply to all the atoms. And we're going to deform the box in the x direction with this rate. And so that's what that fix is doing. You can look it up in the documentation, but we're straining in the x direction, and then we're going to compute the stress that's associated with that strain at every time step and get our stress strain curve. It's a very efficient way of just deforming the box with a particular strain. Instrumentation, this time we're going to make a slightly different call. We're going to measure the strain, which is the current length of the box minus the initial length of the box divided by the initial length of the box. So you'll see on the previous slide that this variable, capital L naught, was the length of the box at the very end of the equilibration run. And so that's for my initial length of the box. Lx, little lx, is the instantaneous length of the box at the particular simulation time step. So this operation is going to give us the strain. I then also want to compute the strain in the x, y, and z directions, and I want to dump this to this file, al_deform.txt, which again MATLAB is going to use to compute our Young's modulus. The thermo, CPU remaining, strains, etc., dumps. This is again just the atom coordinates. Now we have another dump here. So we have our atom coordinates, which has been tagged by dump 1, and then we have a different kind of dump, which is we've tagged by number 2, applying to all atoms, but now not format atom, but format CFG, which stands for a configuration file, which is a different format of dump. So what's neat about this guy is that a configuration file can contain whatever you like. So typically it should contain the atom mass, the atom type, the atom coordinates, but then it can contain a bunch of other things. So we want it to contain the central symmetry parameter for every atom, the energy of every atom, and the instantaneous x, y, and z force in every atom. So why that's nice is we can import it into Ovito, and we can visualize the atom coordinates, and then draw a heat map over the atoms in any of those quantities. So we can color each atom according to its central symmetry parameter, or color each atom according to its x force. So it's a very customizable file format that's sort of more flexible than just dumping the coordinates. So again, you can look up dump in the documentation, look up CFG, and it can tell you exactly what you can do with that. Okay, then here's where all the action happens, calling the Verlet algorithm for 10,000 time steps, and then just cleaning up our fixies and our dumps, because we may want to, in principle, have another run right after this where we want to tag fixies and dumps 1, 2, 3, 4. And that's it. So what we're going to get out here, we're going to get al_eq.txt, which is this file we're going to put into MATLAB recording the approach to equilibrium. And we're also going to have a trajectory of the equilibrium approach of all the atom coordinates. We're then going to have a deformation simulation where we have the atom trajectory, this other fancy trajectory called a CFG, and also this al_deform.txt, which we're going to pull into MATLAB to compute the stress strain curve. Okay, so let's run it and see how it goes. So before you press any buttons, if your machine is slow like mine, this could actually take kind of a long time. It takes sort of 10 minutes to run because there are a lot of atoms. And so what I've suggested is if your system is slow, that you change this line in your input file. Instead of being a region that's 10 angstroms by 10 angstroms by 10 angstroms, you sort of reduce that by a factor of 8 to 0.50505, and so we have much fewer atoms, and so your simulation will run faster. So I recommend that you do that if your system is slow. If you have a nice fast new machine, maybe you'll be okay. Okay, so let's run that if you've not already done so. So again, it will be the call that looks something like this, except it will be al_tensile.in. Okay, so I'm going to edit my line here to be 050505 because I don't want it to take forever. I'm going to save this, and then I'm going to run. Okay, so you can see all the setup here, and now we can actually see our molecular dynamics happening. So this is the equilibration run, and so we're outputting the thermo that we asked for equilibration. And so look at the last column here. You can see that we started at 300 Kelvin because that's how we assigned our Maxwell-Boltzmann. But then the system sort of relaxed, the temperature dropped to 171, and the thermostat kicked in, and it started trying to re-equilibrate us to our desired temperature of 300 Kelvin. And so the temperature is getting a nice approach to 300, potential energy is nice and flat, and our box size, which is Lx, Ly, Lz, these three columns right here, this guy, and this guy, are all identical because it's isotropic, and they've plateaued. Okay, then immediately the deformation simulation kicks in. And so this is now back-to-back simulation where we're taking our equilibrated output and we're deforming it. And so this is going to run for 10,000 time steps. And the thermal coming out, you can see the temperatures at the end there. This is the strain column right here. This is an estimate of the CPU time left. And so the strain is increasing. And you should see that this variable, which is the X stress, is increasing. So stress, strain are both increasing. Then here you actually see a bump. And so when we hit strain of 0.16, there's a massive drop in the stress. And we'll see what that corresponds to in a second. Okay, so that's the sort of text output. Did everyone manage to get that to go okay? Anyone having any severe problems causing big issues? If it's running slow, just cancel it and change that region call to 050505. Okay, let's, in the interest of time, just move on. And so we're going to analyze the approach to equilibrium using MATLAB. And so we're going to use the script here that I provided you in the download folder. So if you pop a MATLAB terminal, navigate to your correct directory and just type al_eq, it will call that M file. And it should make a nice plot. So let's do that. So we want to navigate to Yep, and then we're just going to call ALEQ. It's going to pull in, so you can look in the M file, it's going to pull in this this text file al_eq.txt, and it's just going to make some plots. So it's a pretty simple M file, it's just making some nice graphs, but it's plotting the time and then a bunch of variables. So the box size, you can see, is now plateaued, so the barostat is happy that it's equilibrated just to the pressure we desire. You can see the pressure there, so these are the conjugate variables, sort of volume and pressure. And you can also see that we've hit a nice plateau in temperature at 300 Kelvin. Of course, we see fluctuations around there because they're naturally fluctuations, and the energies of our system have plateaued. So we believe we're at equilibrium. So we now have a nice equilibrated crystal that we're going to tug on. Okay, so approach to equilibrium looks good. If those curves were still moving, we might want to change our run length just by changing the number of steps in our equilibration run. Okay, so that's what the plots look like. So we're pretty happy with that. Now we're going to analyze the deformation using al_deform. So if you go back to your MATLAB window and type deform, it's going to, this MATLAB script is going to pick up al_deform.txt and make this nice plot. So it's going to plot the stress-strain relationship. So this is the strain, this is the stress in the X, Y, and Z direction. As we'll see when we visualize in 1 second, we're pulling in the X direction. That's how we defined our strain. And so the X stress is increasing, whereas the Y and the Z are pretty much constant. And so like we said at the beginning, the Young's modulus is the slope of this line. And so I wrote a little routine into the M file that's going to do a linear regression on the first part of this curve between 0 and 0.05 strain and compute the gradient of this best linear fit, which is the Young's modulus in gigapascals. And so the Young's modulus came out as 62.69, and these are the confidence intervals on that. Yeah?
Could you get out the
You possibly could, yeah, I believe you could. You may have to change your boundary conditions depending on what you want to calculate, but yes, in principle that's available. The other thing to notice here that we, as we were watching the terminal output, we saw that as we hit a strain of 0.16, there was a precipitous drop in pressure, and this corresponds to the homogeneous nucleation of dislocations. And so we'll see that in Novito, that we sort of moved elastically up to here, and then suddenly the crystal couldn't take it anymore, and it started to plastically deform. And so the visualization is going to show us that. Okay, and so this is just what we did. We called AL deform. Looks like this. So we can get two things out of this. We can get the Young's modulus, and we can get the stress for the onset of the termination of elastic deformation and the onset of plastic deformation, which is 8 gigapascals. And so we'd like to visualize this. And so This is another just movie showing you how to visualize this in Ovito. So I'm going to open Ovito. So the Ovito window opens. We did this last time. You get your 4 panes. This is the shortcut button to open a local file. Alternatively, you could go to the File menu and hit Open. Either way works. Okay, so you navigate to the output of your LAMMPS simulation. And so we have our LAMMPS trajectory, but we also have our CFG trajectory. And so this is the more advanced, flexible trajectory that we wrote that contained the central symmetry parameter and the atom energies. And it turns out that the way that this file works is it writes 1 file per frame. And so that's why they're all labeled according to the frame number. So you just select the first one. So it was indexed frame 0, so you click on that and open it. Ovito was smart enough to know that there are probably a bunch of those files in the same directory, and so you can immediately see along the slider at the bottom that there are 80 of these guys. And so these are the outputs of every frame, or every 125, or how many frames you asked it to dump from the deformation trajectory. Okay, now we're going to do something a little more advanced in Ovito. So the first thing we're going to do is go up to this action window up the top here. So the best way to think about Ovito is a pipeline. And so down at the bottom here is the data, and up at the top here is the display. And between those two things you can apply different operations, so different visualization options. And so what you want to do is click on the topmost thing in the input data, which is just the data files, and then click Add Modification. And so we're going to click here, and then we're going to click Add Modification. So big list of different modifications. And so this is now modifying the data before it goes to the display. And so the modification that we're going to pick is color coding. So this is typically the most common one that you pick. So you click on color coding, and then you get this nice panel down here whereby you can color your atoms in your box by whatever you want. So what's nice about the CFG file is that we've dumped things that are useful to color the atoms by, central symmetry parameter, or energy. And so right now they're colored by mass, which is not useful because they're all identical. So let's change that. So the CFG file contained various things. It contained their positions. It contained some forces. You could ask it to contain other things. But the one that we like is central symmetry. So let's click on that guy. And then we need to reset the range. And so we know the central symmetry goes from like 0 to maybe 23. It turns out a good range to set it to is like 0 to 12. So just change the range of the color scale. And then we're just going to hit play. Okay, so the simulation is evolving. The one to watch is this one. We're stretching in the X direction, and so you're going to see that the box is going to be strained in this direction, and we're going to color the atoms according to central symmetry. So they're all blue, they're all nice, happy FCC with some fluctuations, bigger and bigger and bigger, then suddenly disaster. So the dislocation homogeneously nucleates, and you can see that moving across the box. Maybe looking at the perspective one is a little more useful. You can see the dislocation planes. Okay, so this is good, but it's a little hard to see because there's this bunch of sort of blue FCC atoms in the way of the dislocation planes. And so we can add a couple of other modifications to the Ovito pipeline in order to better visualize these by isolating only those atoms that are deviant from the central symmetry. And so what we do is we add the modification. So let me go back one more. So what we've done is that we've clicked on the input data, and we're going to modify the pipeline before we get to color coding. So add modification, expression select. This allows us to select atoms based on a particular quantity, and so the quantity we're going to select on is central symmetry. So you just do it, write a Boolean. Central symmetry has to be less than 4. So if your central symmetry is less than 4, you get selected. Now what we're going to do is delete them. So if you are selected by that operation, we're going to choose delete selected particles. And so they get removed from the visualization before we hit color coding. Okay, so now we're going to play the simulation, visualizing only those atoms that have central symmetry greater than 4. And so this is a nice visualization because you can see very clearly the dislocation planes as they homogeneously nucleate. We've removed all those atoms that remain FCC. Okay, so this is great, but this is all internal to Ovito. So perhaps we'd like to dump this to an output file that we would put in a presentation to show folks what great simulation that we did. So I'm going to select this perspective window to be the one that I'm going to dump to an output file. I'm going to rotate the perspective just using the mouse. And I'm going to go up to the bar up here. This is the render settings, and I don't just want a single flip frame, I'm going to want the complete animation. And I'm going to give the file a name, so you can call it whatever you want. And I'm going to save it as a GIF. Okay, so whatever is going to be seen in this window is now going to be rendered to this GIF. And so then we go up to the top menu bar and hit the render, and then Ovito does the rendering for us. So it's taking whatever is living in that window and putting it into this GIF file. Okay, so we see the dislocation planes. Okay, then we hit close that window, close Ovito, and we see that our file is now living on the desktop. We called it deform.gif, and so we can now import that into our presentation. It turns out a nice way to visualize GIFs is using a web browser, so I'm just going to navigate to the desktop and open it using Safari, which is the Apple web browser. So open using Safari, my GIF file. So you can open it using whatever program you want. And so then it pulls it into a Safari tab, and then you have your GIF. And so you could then use that in your presentation or whatever you wish. Okay, so that's sort of slightly more advanced features of Ovito. It's a very nice engine. So just last slide, so then comparing to experiment, how did we do? Young's modulus from LAMMPS was around 62, experimentally was about 69, so pretty good, we're within 10%. Yield stress, LAMMPS said that you start to nucleate dislocations at 8,000 megapascals, 8 gigapascals. Experimentally it's more like 10 megapascals, this is horrible, so we had a horrible estimate of this, so why? Well, Young's modulus was good, within 10%. Really, we should check convergence as a function of system size to make your system bigger and see if your answer changes. Yield stress is off by 3 orders of magnitude. Why? We did it in a perfect crystal. So this is the yield stress for homogeneous dislocation nucleation. Really, in practice, things nucleate heterogeneously due to the presence of defects, dislocations, etc. So if you wanted to estimate a closer estimate to experiment, you would have to build your crystal with some defects built into it and do exactly this simulation. Okay, and then just last, very last words, which is how could we incorporate that into the sort of an ICME paradigm? Well, we've used molecular dynamics at this length scale to estimate the Young's modulus, which we might then import into a finite element model at a larger scale. So we might design a finite element analysis simulation, and we could dial in the value of the Young's modulus that we computed from our molecular dynamics simulations. Why is this useful? Well, maybe you're studying a new material that hasn't been experimentally characterized, or perhaps a material that's hard to characterize experimentally, or is too dangerous to characterize experimentally, or is under conditions where it's very difficult to analyze. So in a nuclear reactor or at very high temperature or pressure. In which case you could use MD to get the parameters to input into a finite element simulation and then do things over length scales of say centimeters for seconds. So integrating into this ICME paradigm. And so with that, that's sort of all I had for you today. We'll stick around and answer any questions you might have, and we'll get Neil to put these slides up for you to download. So thanks very much for your attention, and I hope you guys find this useful.